The human imagination, unbound by physical limits, often reduces the cosmos to a neighbourhood. Consider Proxima Centauri, our celestial next-door neighbour, a mere 4 light-years away. Its small rocky planet Proxima b orbits within the so-called habitable zone, a region where liquid water might exist. For a fleeting moment, one can almost envision a future probe gliding through its alien dawn, sending back images of another world. Yet this comforting dream conceals a profound and often uncomfortable truth. In the vast chronicle of human achievement, we have yet to truly depart our own solar system. With every new astronomical discovery, the stark reality becomes clearer. Reaching Proxima b may remain an unattainable feat. Not for our generation, nor perhaps for any civilization we might become. A star seemingly within reach, yet separated by a chasm of almost incomprehensible scale. For millennia, humanity has been captivated by the distant, unreachable fires of the night sky. Each twinkling beacon whispers of worlds beyond our own. Among them, Proxima Centauri stands out by every astronomical metric as the closest star to our Sun. Situated just over 4 light-years distant, it is a diminutive member of the triple star system known as Alpha Centauri, a system that defines our immediate galactic neighbourhood. In cosmic parlance, this is indeed next door. However, the phrase nearest star can be deeply misleading. Even proximity in the language of the universe denotes a distance almost beyond human comprehension. Proxima Centauri itself lies approximately 40 trillion kilometres from Earth. The term light-year often loses its true impact. It represents the distance light travels in 1 year, a journey undertaken at an astonishing 300,000 kilometers per second, a speed sufficient to circumnavigate Earth more than 7 times in a single second. Yet even at this absolute cosmic speed limit, light itself requires 4 full years to traverse the immense gulf between us and Proxima Centauri. For context, the fastest spacecraft ever constructed by humanity, NASA's Parker Solar Probe, achieves speeds exceeding 600,000 kilometers per hour. At this incredible velocity, it would still demand over 7,000 years to reach Proxima Centauri, a duration longer than the entirety of recorded human history. This disparity delivers the first and perhaps most humbling lesson of interstellar travel. Distance in space is not what we perceive. The sheer scale of the cosmos shatters our terrestrial sense of proportion. We are accustomed to measuring in terms of roads, countries, or even planetary diameters. Between the stars, however, lies an emptiness that defies these instincts. Our own solar system, which already feels staggeringly vast, is merely a tiny, fragile bubble, adrift in an endless ocean of void. Despite these formidable challenges, the aspiration to reach Proxima Centauri has crystallized into one of humanity's most audacious scientific objectives. It stands as a testament to both our technological ambition and our innate curiosity. For decades, scientists, engineers, and visionaries have wrestled with the same fundamental inquiry. Could we ever dispatch a probe there? Could we even once truly touch another star system? The answers are intricate, multifaceted, and still largely theoretical, yet the relentless pursuit has undeniably begun. Pioneering initiatives like Breakthrough Starshot envision a radical departure from conventional propulsion. They propose leveraging immense ground-based lasers to propel a minuscule spacecraft no larger than a postage stamp to a significant fraction of the speed of light. If this audacious concept were to succeed, such a miniature traveller could theoretically reach Proxima Centauri in a mere 20 years. For the first time, a human-made object might bridge the vast interstellar gulf within a single human lifetime. Yet for the present, this vision remains firmly within the theoretical realm, a complex blueprint for a potential future. The underlying physics are largely sound, but the engineering hurdles are staggering. The required laser system would need to generate more concentrated power than any existing technology can currently provide. Furthermore, the miniature spacecraft would have to endure collisions with microscopic dust grains at velocities that would instantly vaporize conventional materials. even the critical act of slowing down near its destination, if the mission aimed for anything more than a fleeting flyby, would necessitate entirely new physics and propulsion concepts. Every intricate detail of this proposed mission underscores the extreme difficulty inherent in interstellar travel. In a profound sense, it is precisely this monumental scale of difficulty that imbues the dream with its extraordinary meaning. Confronting such apparent impossibility reveals something fundamental about our species, our insatiable hunger to explore even when the odds appear overwhelmingly stacked against us. It is the same primal impulse that once compelled our ancestors to traverse unknown oceans, or that drove us to dispatch probes into the enigmatic darkness beyond Pluto. Still, the phrase "a star within reach" can indeed feel like a linguistic deception. Even electromagnetic signals, which travel at the universe's absolute speed limit, require 4 years to make a one-way journey. This means that if a spacecraft were to transmit a message home immediately upon arrival, Earth would not receive that communication until nearly a decade after the probe's initial departure. Assuming, of course, it managed to arrive at all. The reality is that the distances separating stars are so immense, they stretch the very concepts of travel and communication to their breaking point. The sheer scale of interstellar space forces us to confront not only the limitations of our current technology, but perhaps more profoundly the limits of our collective patience. The void between stars is so vast that even the fastest known phenomena appear agonizingly slow. When this realization truly sets in, the night sky transforms. Every star becomes a silent, stark reminder of the cosmic wilderness that lies between them, a silent void where distance itself stands as the ultimate unyielding barrier. Proxima Centauri itself is not a brilliant beacon like our Sun. It is a faint red dwarf, substantially smaller, cooler, and considerably dimmer. If one were to hypothetically stand on a planet orbiting it, the sky would likely be painted in a perpetual dull red glow. And yet this small, quiet star has captured human attention more intensely than most others. This is because in a universe where almost everything feels unimaginably distant, even a faint spark nearby feels uniquely special. Orbiting this humble star, astronomers have confirmed at least one exoplanet, Proxima b, a world that under a very specific and perhaps unlikely confluence of conditions might harbour liquid water. Whether it could genuinely support life remains a profound unknown, but its mere confirmed existence has irrevocably altered our perception of Earth's place within the vast tapestry of the galaxy. It serves as a potent indicator that other worlds, potentially even habitable ones, are not merely abstract, faraway dreams. They are tangible realities awaiting discovery just beyond the current grasp of our technology, yet never beyond the reach of our boundless curiosity. The invisible wall beyond the Sun. Leaving our solar system sounds deceptively straightforward. Simply maintain course, fly away from the Sun, and eventually you'll reach the space between stars. In reality, however, that boundary is not delineated by a visible line or an observable border. There is no cosmic gate, no tangible edge to photograph. The true frontier of our solar system is an invisible dynamic region defined not by solid objects, but by fundamental forces. Scientists refer to it as the heliopause, representing one of the most critical yet least understood thresholds in all of space exploration. To comprehend the heliopause, one must first grasp the nature of our Sun. Our star is not merely a colossal sphere of incandescent light. It functions as a powerful, ceaseless engine constantly emitting a torrent of charged particles. A solar wind composed primarily of protons and electrons. This solar wind expands outward in all directions, inflating an immense invisible bubble that envelops everything within our planetary system. Every planet, every asteroid, every comet we can name exists within this protective, albeit invisible bubble of solar influence. The solar wind continues its outward journey until it eventually encounters the faint, diffuse gas drifting between other stars, the interstellar medium. The heliopause marks the precise boundary where the outward pressure of our Sun's wind finally yields to the subtle, yet persistent pressure of this interstellar gas. this boundary, far from being close, is unimaginably distant. The heliopause lies more than 120 times farther from the Sun than Earth does. While sunlight takes approximately 8 minutes to reach Earth, it requires over 16 hours to arrive at the heliopause. It extends far beyond Pluto, beyond the Kuiper Belt, into a region so remote that the Sun's light there is reduced to little more than a faint distant glow. Traversing this immense distance poses challenges far greater than any journey humanity has ever undertaken. Even calling it an edge can be misleading, as the heliopause is not a fixed rigid surface. It breathes, moves and ripples in concert with the solar cycle. When the Sun becomes more active, unleashing flares and coronal mass ejections, its wind intensifies, pushing this boundary further outward. Conversely, when solar activity wanes, the wind weakens and the heliopause drifts inward. It expands and contracts a living membrane over the course of years. Its shape is also far from perfectly spherical. The persistent pressure of the interstellar medium, the thin gas between stars, exerts greater force on one side, subtly distorting the bubble, much like a balloon gently squeezed by unseen fingers. For a long time, this dynamic border existed solely as a theoretical construct. The first tangible encounter humanity had with this invisible wall occurred in 2012, when NASA's Voyager 1 spacecraft, launched way back in 1977, finally passed through it. After an astonishing 35 years of continuous travel, the probe transitioned from the Sun's protective domain into the realm of true interstellar space. Yet even this monumental achievement was not immediately clear-cut. Voyager famously carried no camera to capture the moment. There was no photographic evidence of the boundary, no glowing horizon. Instead, scientists had to meticulously interpret the subtle signatures hidden within the probe's data, sudden shifts in charged particle counts, enigmatic bursts of radiation, a distinct drop in the solar wind's intensity. For months, a scientific debate ensued regarding whether Voyager had truly exited the heliosphere or merely grazed its outermost edge. However, a definitive shift in cosmic ray intensity ultimately confirmed the crossing. Humanity had for the first time extended its reach beyond the heliopause. A machine forged on Earth had stepped into the profound void between the stars, and what it discovered there was far from emptiness. The region beyond the heliopause is not a sterile vacuum. It is populated by particles originating from other stars by cosmic rays that have traversed millions of years through the galaxy. The environment proved to be denser than theoretical models predicted, and its magnetic fields twisted in surprisingly unpredictable ways. Voyager 1's instruments, remarkably resilient despite being decades beyond their intended lifespan, continued to transmit invaluable clues about this mysterious realm, revealing that even just outside our solar system, the universe behaves with unexpected intricacies. When Voyager 2 subsequently crossed the heliopause, it provided further confirmation the boundary is not uniform. On its side of the solar system, the pressure and particle density were notably higher. This critical data informed scientists that the interstellar medium itself is not homogeneous. It is a dynamic environment alive with fluctuations akin to unseen waves on a vast cosmic ocean. It is a humbling realization that both Voyager spacecraft, the farthest human-made objects from Earth, are still barely past the shoreline of interstellar space. Even after nearly half a century of travel, they have only just stepped beyond the immediate influence of our Sun. To put this into perspective, if one were to scale the solar system down such that Earth and the Sun were just 1 meter apart, the Voyagers would be less than 100 meters away. In this same scaled model, the next star Proxima Centauri would still be an astonishing 400 kilometers further. This comparison alone vividly illustrates the immense and profound loneliness of the space beyond the heliopause. The heliopause represents the definitive border between our Sun's territory and the wider galaxy. Inside its confines, every aspect — magnetic fields, radiation, cosmic particles — is sculpted by the solar wind. But beyond it, these local rules yield to the collective, more pervasive forces of the Milky Way itself. It is as if every star possesses its own protective bubble, and the space between these bubbles constitutes the very fabric of interstellar space. To transition from one stellar bubble to another is to move from one distinct physical environment to an entirely different one, a journey no human has ever made. This is precisely why crossing the heliopause is a far more significant leap than travelling from Earth to Pluto. From our home planet to the outermost worlds, we remain under the influence of the same star within its protective field. Even at Pluto's orbit, the sun's wind exerts a faint pressure, and its magnetic field still shields spacecraft from the brunt of cosmic radiation. But beyond the heliopause, that vital protection dramatically diminishes. Spacecraft venturing into this realm confront the full unforgiving harshness of interstellar particles, which can irrevocably damage sensitive electronics and slowly erode materials at an atomic level. If humanity ever hopes to dispatch a crewed mission this far, it will necessitate shielding and communication systems fundamentally unlike anything we have ever conceived. Then there is the issue of velocity. The Voyagers travelling at over 60,000 kilometers per hour still require decades to reach the heliopause. Future probes would need to achieve speeds many times greater to meaningfully explore the vastness beyond. But such extreme velocity introduces its own set of profound hazards. At interstellar speeds, even a microscopic grain of dust transforms into a deadly projectile. The space between stars, though seemingly empty, is thinly sprinkled with microscopic debris that could tear through a spacecraft moving at a fraction of light speed. This invisible minefield elevates the seemingly simple act of leaving our solar system into an engineering challenge of epic proportions. NASA's interstellar probe concept envisions a spacecraft specifically engineered not just to cross the heliopause, but to meticulously study the space far beyond it. It would aim to travel faster than any probe before reaching hundreds of astronomical units from the Sun within 50 years. Its primary mission would be to meticulously map the true dynamic shape of the heliosphere, directly measure the interstellar medium with unprecedented precision, and perhaps glimpse the faint glow of nearby stars with new discerning eyes. Yet even this immensely ambitious plan would still largely confine us to our immediate stellar neighbourhood. The distance to the next star would remain so vast that even the fastest conceivable probe could only inch toward it century after century. For billions of years, every atom comprising Earth, every breath of air, every ray of sunlight existed entirely within the protective bubble of the heliosphere. When Voyager crossed that invisible line, it became the very first artifact from our world to enter true galactic space. That singular moment may indeed represent one of the most profound turning points in human history. It served as undeniable proof that our reach, however minuscule, can indeed extend beyond the cradle of our nurturing star. Standing here on Earth, it remains incredibly difficult to conceptualize what outside truly signifies. The edge of the solar system is not a place anyone could physically see or touch. It is a dynamic frontier defined by intricate interactions of energy and motion. Somewhere out there, more than 20 billion kilometers away, Voyager 1 continues its solitary drift through that strange alien environment, its faint, persistent signal still whispering home across the cosmic dark. Voyager's long goodbye. The Voyagers were never engineered with the ambition of reaching another star, nor were they ever intended to endure for such an extraordinary duration. When they first departed Earth, their initial mission lifespan was projected to be a mere 5 years, just enough time for crucial flybys of Jupiter and Saturn. Yet against all odds, their intricate systems persevered. Their power supplies held and their scientific instruments continued to transmit invaluable data long after their primary objectives were fulfilled. Over time, mission controllers realized these resilient spacecraft could accomplish far more than anyone had ever imagined. Each new milestone they achieved became another poignant goodbye. First to the familiar planets, then to the solar system itself, and finally to the direct influence of the Sun. Their faint signals now require more than 22 hours to traverse the vast distance to Earth, travelling at the very speed of light. When engineers dispatch commands to the probes, it takes almost a full day for the instructions to arrive, and another full day for any reply to return. The radio waves themselves are incredibly attenuated. By the time they reach our planet, their signals are weaker than the kinetic energy of a single snowflake striking the ground. Yet remarkably, the colossal antennas of Earth's deep space network, a global array of massive radio dishes situated in California, Spain and Australia, continue to meticulously listen for them day and night. Each faint transmission is painstakingly decoded its bits of data, revealing minute changes in temperature, magnetic fields and cosmic radiation. Every single byte is critically important, for each one originates from a realm no human will likely ever visit. Even now, Voyager 1 persistently measures the enigmatic environment of interstellar space. It meticulously senses the density of charged particles, registers the subtle hum of magnetic fields, and tracks the minute variations in cosmic rays that permeate the galaxy. The spacecraft itself, however, is undeniably aging. Its nuclear power source, a small plutonium generator, is steadily depleting its energy reserves. Each year, engineers are compelled to selectively deactivate another instrument to sustain the remaining ones. One by one, the sensors are falling silent. By the 2030s, both Voyagers are projected to fall silent forever. When that moment arrives, they will continue their outward trajectory, but without a voice. Their transmitters will finally fade, their instruments will cool, and their tiny onboard computers, less powerful than a basic digital watch, by today's standards, will cease their tireless ticking. They will become cold, inert relics drifting silently through the galaxy, each carrying its golden record, a message specifically designed for any intelligent entity that might one distant day discover them. These records contain greetings in dozens of human languages, iconic images of Earth's diverse landscapes and its people, and the sounds of our vibrant world, the laughter of children, the chirping of birds, the rush of wind and waves. It is humanity's quiet handshake extended into eternity, yet their agonizingly slow pace does not diminish their profound significance. Every kilometre they traverse adds a new chapter to our ongoing story of cosmic exploration. They have unequivocally demonstrated that venturing beyond our star's direct influence is not the journey's conclusion, but rather the exhilarating commencement of an entirely new one. For the very first time, we possess direct data from interstellar space. Voyager's meticulous measurements have fundamentally reshaped how scientists conceptualize the elusive boundary of our solar system. Eventually, these intrepid probes will pass near other stars. In approximately 40,000 years, Voyager 1 will approach within 1.6 light-years of a small star named Gliese 445 in the constellation Camelopardalis. While not close enough for a visit, it will mark its first passage through another sun's immediate neighbourhood. Voyager 2 will embark on a different trajectory, heading towards the constellation Sagittarius. In the fullness of time, both spacecraft will transform into interstellar fossils, tiny silent objects wandering the vast expanse of the Milky Way. A red star with a secret. If our sun embodies a blazing perpetual furnace, Proxima Centauri resembles a small campfire struggling valiantly against the wind. Its light is intrinsically weak, tinted a deep red, and its warmth would barely reach any world circling it. Yet within that faint ruddy glow there exist planets, and on one of them perhaps a delicate confluence of conditions for something more complex. Astronomers first definitively confirmed Proxima's status as our Sun's closest stellar neighbour in 1915. Initially it seemed unremarkable, merely another dim red star amidst countless billions. But over the ensuing decades it evolved into something greater, a potent symbol. If humanity were ever to reach another star, this would be the primary target, the first true port of call in the boundless ocean of interstellar space. Then, a century after its initial discovery, a revelation ignited human curiosity anew. In 2016, scientists utilizing a telescope in Chile announced the confirmation of a planet orbiting Proxima Centauri. Proxima b was found to be comparable in size to Earth, and crucially situated within the star's habitable zone. This announcement sent palpable shockwaves through both the scientific community and the collective human imagination. The immediate inability to travel there seemed almost irrelevant. The sheer idea alone was sufficient. For decades prior, the search for exoplanets had largely been a numerical endeavour, focused on detecting hundreds, even thousands of worlds around distant suns. But Proxima b felt intrinsically personal. It was close enough that were one able to conceptually leap from star to star, this would be the very first stop. Suddenly, the notion of another Earth-like world no longer felt like an abstract concept buried deep within telescope data. It felt almost tangible within grasp. Still, the reality of Proxima b is far from idyllic. Red dwarf stars such as Proxima Centauri are notorious for being unpredictable and often violent. Their surfaces seethe with intense magnetic storms that unleash torrents of high-energy radiation into space. Proxima's flares can become so powerful they momentarily outshine the entire star for minutes at a time. If Earth orbited such a star, our protective atmosphere would likely be stripped away, our oceans boiled, and our skies saturated with lethal radiation. Scientists now strongly suspect that Proxima b may endure precisely this kind of relentless bombardment. It orbits its star so tightly that a year on Proxima b lasts a mere 11 Earth days. At such proximity, it is almost certainly tidally locked, meaning one hemisphere perpetually faces its star basking in an eternal scorching day, while the other remains trapped in endless frigid night. The day side could be mercilessly scorched by constant solar flares. The night side could be a desolate expanse of frozen airless terrain. In between these extremes, perhaps along a narrow twilight band, there might theoretically exist a region where temperatures are mild enough for liquid water, assuming the planet retains any water at all. And yet, even confronted with these grim conditions, the scientific community has not abandoned hope. Because if life can manage to exist there in such a harsh alien environment, it would profoundly imply that life could potentially exist almost anywhere in the cosmos. Red dwarfs like Proxima are, after all, the most common stars in the universe, constituting over 3/4 of all stellar bodies. If even a small fraction of them can support life, then the universe itself could be teeming with it. The Proxima Centauri system might also harbour more than just one planet. Some ongoing studies have hinted at the potential presence of a second, more distant world, tentatively named Proxima c. While its existence remains unconfirmed, it would orbit significantly farther from the star, rendering it an icy cold realm. But even this incomplete picture paints a small yet complex solar system, one that subtly mirrors our own, in miniature a dim star, a possibly habitable world, and perhaps another frozen one beyond. Observations consistently reveal that Proxima's surface flickers continuously. Its brightness can fluctuate dramatically in a matter of seconds. Every time telescopes are directed towards it, something appears to be in motion. A flare, a pulse, a brief surge of light. It serves as a potent reminder that even at its faintest, a star remains alive in its own tumultuous way. A boiling sphere of energy and unpredictable chaos. From our vantage point, over 40 trillion kilometers distant, we can barely discern the intricate details. Proxima Centauri manifests merely as a single point of red light. Yet through that tiny distant dot, we have successfully detected the gravitational pull of unseen planets, meticulously measured its powerful flares, and observed the subtle shifts in its stellar rhythm. We have come to know this faint ember almost as intimately as an old neighbour. When scientists detect a flare, they discern danger. When they meticulously measure its faint light curve, they perceive possibility. When they refine their instruments to pinpoint another planet, they discover a compelling reason to continue their exhaustive search. And within all these endeavours there persists that quiet yet unyielding hope that somewhere near that ruddy glow something else might be looking back. The illusion of the habitable zone. When scientists announced that Proxima b resided within its star's habitable zone, the phrase rapidly proliferated. News headlines trumpeted it as an Earth-like world, with some even hinting at its potential to host life. The very words habitable zone resonate with inherent promise. They evoke images of shimmering oceans, glowing skies, and conditions conducive to life. Yet this is one of the most widely misunderstood concepts in modern science. The term habitable zone does not confirm a planet's actual habitability. It merely implies that in theory, if a planet possessed the correct atmospheric composition and surface pressure liquid water could exist on its surface. It is fundamentally an educated guess based solely on distance from its star, not on observed reality. It conveys no information about the planet's true nature, whether it has an atmosphere, oceans, or even solid ground. It is a thin theoretical line drawn on a cosmic map indicating where life might survive, not where it definitively does. For Proxima b, that line is far more illusion than promise. The planet orbits extremely close to its red dwarf star. If it were orbiting a star like our own Sun, it would be scorched beyond recognition. However, Proxima Centauri's inherently faint glow renders that tight orbit theoretically just warm enough for water. In theory. Red dwarf stars are inherently unstable, and Proxima Centauri is one of the most volcanically active among them. Its flares are thousands of times more energetic than those produced by our Sun, and they occur with alarming regularity. If Proxima b ever possessed a substantial atmosphere, it may very well have been completely stripped away by now. Without that crucial protective layer, liquid water cannot persist. It either freezes solid or rapidly evaporates into the vacuum of space. And if there is no water, the very concept of habitability vanishes entirely. The habitable zone then becomes a hollow term, a purely mathematical circle drawn around a decidedly dangerous star. Astronomers are of course fully aware of this nuance. When they discuss habitability, they employ the term cautiously as an initial clue, never as a definitive conclusion. But beyond the stringent confines of scientific research, the word often takes on a life of its own. It powerfully feeds the human imagination. It is far easier to envision an ocean world than to contemplate a scorched, airless rock. The phrase habitable zone offers a small, comforting illusion, a sense that life could be common, that Earth is not uniquely alone. But the deeper truths of science often lie hidden beneath layers of hope and deceptive simplicity. The challenge lies in the fact that genuine habitability is infinitely more complex than mere distance. For a planet to truly support life as we comprehend it, a demanding checklist of conditions must align with exquisite precision. It requires not only water, but also an atmosphere sufficiently thick to trap heat. It must possess robust protection from lethal radiation, most likely in the form of a magnetic field generated by a molten active core. Its orbit must be stable, precluding wildlife extinguishing swings in temperature. Its rotation must be finely tuned to maintain a balanced global climate, preventing one side from being locked in perpetual night. And perhaps most critically, these conditions must endure with remarkable stability for billions of years, a timescale long enough for life to originate, evolve and persist. We can infer some of these factors from afar, but most remain largely unknown. When we detect a planet like Proxima b, what we truly uncover is a shadow, a dim signature in starlight that indicates its existence and approximate mass. We possess no direct knowledge of its appearance, its precise composition, or even whether it genuinely possesses an atmosphere. For all we know, it could be a barren, scorching rock akin to Mercury, or a perpetually frozen world like Pluto. Even within our own solar system, the concept of a habitable zone proves misleading. Venus, for instance, resides well within the Sun's habitable zone, positioned close enough that liquid water should theoretically be possible. Yet its surface is a hellish wasteland, hot enough to melt lead, shrouded in a choking atmosphere of carbon dioxide and corrosive sulfuric acid clouds. The crushing pressure there would obliterate any spacecraft within minutes. Earth and Venus are cosmic neighbours nearly identical in size, yet one teems with vibrant life while the other burns beneath a toxic perpetual sky. The habitable zone alone cannot account for such a radical divergence. Mars too challenges the concept. It lies near the outer edge of the Sun's habitable zone and may once have harboured rivers, lakes, and even oceans. Today, however, it is a frozen desert, its thin atmosphere incapable of retaining warmth. Water still exists there, locked as ice beneath the surface, but the planet is far from a living world. The lesson is abundantly clear: being in the right place does not inherently guarantee the right conditions. In a profound sense, the habitable zone is akin to a desert mirage, a tantalising indication that water could be nearby, but never definitive proof that it actually is. It serves primarily to help scientists judiciously narrow their search, pointing to where to look more closely. But what we often uncover when we do look often shatters the illusion. Proxima B's case is rendered even more uncertain by the volatile nature of its star. Red dwarfs, while burning slowly and potentially lasting for trillions of years, experience a chaotic youth. If life ever does emerge around such stars, it must either evolve extreme protective mechanisms or originate long after the star has settled into a quieter phase, which itself could take billions of years. We do not yet possess the knowledge to determine if such evolutionary pathways are truly possible. Still, the idea that life could exist around red dwarfs remains intensely enticing, precisely because these stars are so incredibly common. Their habitable zones, however unstable, represent countless billions of potential worlds. Even if only 1 in a million manages to tenaciously cling to its atmosphere, the universe would still harbour billions of potentially life-bearing planets. When powerful telescopes like the James Webb Space Telescope, JWST, or future observatories are aimed towards systems like Proxima Centauri, they are not searching for shimmering oceans or verdant forests. They are meticulously seeking the subtle signs of an atmosphere, the faint traces of specific molecules like oxygen, methane, or carbon dioxide that might betray the planet's underlying chemistry. A single characteristic spectral line in the starlight could suggest the presence of an atmosphere. From that, scientists can begin to infer whether liquid water might still exist. It is detective work on an unparalleled cosmic scale, utilising light itself as the sole invaluable witness. And yet, even if JWST or future telescopes successfully detect what appears to be an atmosphere, we will still lack definitive knowledge of the planet's true habitability. It could possess clouds of dense hydrogen instead of breathable oxygen, or be perpetually shrouded in a thick toxic smog. It could be a world of steaming acid or endless frigid ice. From 4 light-years distant, our view remains a mere whisper, never a clear, unambiguous picture. Perhaps the very word habitable reveals more about our own terrestrial biases than about other worlds. It reflects our profound longing for familiarity. We instinctively imagine other planets adorned with blue skies, rocky ground, and gentle sunlight, because these are the very conditions that fostered our own existence. But life in its boundless ingenuity might not necessitate any of these precise conditions. It could conceivably exist in forms we can barely conceive, deep beneath ice within the pores of rocks or suspended within atmospheric clouds. Our current definition of habitability may be inherently too narrow, unduly shaped by the singular experience of one world. Still, the term retains its utility because it provides a crucial starting point. It serves as a rudimentary map drawn by our current scientific understanding, indicating where the odds for life might be marginally more favourable. It doesn't promise life, but it steadfastly fuels our relentless search. Our fastest ships are still drifting. When a probe is dispatched to Mars, we patiently await its arrival for a few months. A journey to Jupiter might require several years. These timescales feel manageable. We can quantify them, plan around them, and often live to witness the mission's outcome. But when we begin to speak in terms of tens of thousands of years, we utterly transcend the realm of human experience. A journey to Proxima Centauri using current technology would not merely outlast a single civilization, it would outlive multiple ones. Empires would rise and fall, languages would evolve and vanish, continents would shift beneath ice and sea. all while the probe continued its silent drift through the cosmic dark, still not halfway to its destination. A probe like Voyager vividly illustrates the fleeting nature of a human lifetime. The spacecraft's radio signal now takes over 22 hours to reach Earth. Every message transmitted from Voyager today is a whisper from yesterday, already ancient by the time it arrives. When we listen to Voyager's signal, we are in essence listening to a machine speaking to us from the distant past. At Voyager's current velocity, it covers approximately 500 million kilometers per year, a figure that sounds impressive until one realizes that a single light year spans almost 10 trillion kilometers. This stark comparison reveals that Voyager 1, despite its decades of continuous travel, has traversed less than 500th of a single light year since its departure from Earth. The Voyagers, the Parker Solar Probe New Horizons, they're all like drifting seeds, each carrying a precious fragment of our curiosity into the boundless dark. Long after every mission controller, every engineer and every observer on Earth has passed into history, those probes will continue their outward trajectory, carrying with them the enduring memory that someone once yearned to see what lay beyond. It is tempting to believe that future technological breakthroughs will fundamentally alter everything, transforming thousands of year journeys into mere decades. Concepts such as nuclear pulse propulsion, fusion drives, or even laser sails are frequently imagined as ultimate solutions to this formidable problem. Yet even these audacious ideas, as bold as they are, confront monumental challenges. They demand energy sources that currently do not exist, materials capable of withstanding unimaginable stresses and engineering precision that borders on the impossible. If even one of these concepts were to function flawlessly, if we could somehow accelerate a probe to 1/10 the speed of light, the journey to Proxima Centauri would still require more than 40 years, essentially a full human lifetime. That in essence defines the true scale of the challenge. Our fastest ships today are in cosmic terms merely crawling compared to what is truly needed. They are heroic endeavours, but minuscule against the backdrop of interstellar distance. To reach even the nearest star, we would have to push far beyond everything we currently comprehend about propulsion power generation and perhaps most critically human patience. For now, our voyages remain largely symbolic, gestures of exploration, not yet true journeys to tangible destinations. The hard ceiling of rocket physics. Every single rocket that has ever departed Earth, from the earliest primitive test flights to the colossal Saturn V that transported humans to the moon, has been powered by the same fundamental principle, the controlled combustion of fuel. The underlying concept is deceptively simple, understandable even to a child. A rocket expels mass in one direction, and in doing so generates motion in the opposite direction. This is Newton's third law of motion, the immutable rule that every action elicits an equal and opposite reaction. It is an elegant, robust, and profoundly reliable principle that has propelled us farther than any other propulsion method ever conceived. However, it also comes with an inherent unyielding hard ceiling, a fundamental limit that no amount of engineering genius can truly circumvent. The core of the problem lies in the immutable laws governing how rockets function, the intricate mathematics of thrust mass and fuel consumption. A chemical rocket, by its very design, must carry every single component required for its propulsion, its fuel, and its oxidizer. It cannot replenish in the vacuum of space, nor can it draw power from the surrounding void. To achieve greater velocity, it must consume more fuel. But the more fuel one adds, the heavier the rocket becomes, which in a cruel feedback loop then demands even more fuel to propel that additional mass. It is a self-perpetuating cycle, one that mercilessly punishes ambitious design. Every extra kilogram of propellant contributes to the total launch weight, resulting in diminishing returns from each incremental improvement. This fundamental relationship is precisely described by the rocket equation, first formulated in the 19th century by Konstantin Tsiolkovsky. It precisely quantifies the maximum change in velocity a rocket can achieve based on the amount of fuel it carries and the speed at which that fuel is expelled, what engineers term the exhaust velocity. For chemical rockets, this exhaust velocity is inherently constrained by the finite energy released during chemical reactions. These reactions are exceptionally well understood. Hydrogen and oxygen, when combusted together, produce some of the highest chemical energies known. The resultant maximum exhaust velocity is approximately 4.5 kilometers per second. While impressive, this represents a fundamental ceiling built into the very laws of chemistry. Regardless of the ingenuity of the design, one simply cannot extract more energy from those atoms than nature itself permits. To escape Earth's formidable gravitational pull, a spacecraft must attain a velocity of at least 11 kilometers per second, more than double what direct chemical combustion alone can produce. Rockets achieve this by employing a technique called staging, wherein empty fuel tanks are jettisoned to shed mass as the vehicle ascends. The iconic Saturn V, for instance, utilized 3 distinct stages each, progressively smaller and lighter than the last to achieve orbit, and eventually propel astronauts beyond Earth. However, this clever technique does not fundamentally alter the underlying physics, it merely stretches its application. No matter how many stages are added, or how lightweight the structural components are made, the inherent energy limits of chemical reactions remain constant. Once a rocket has expended its fuel, it is condemned to coast indefinitely at whatever velocity it achieved. This is precisely why the fastest spacecraft ever launched by humanity, even those incorporating the most efficient designs, all invariably peak within roughly the same range, tens of kilometers per second. Pushing beyond this range demands exponentially greater energy. Doubling a rocket's speed does not simply mean doubling its fuel, it necessitates multiplying it many times over. In fact, to double one's speed, you might require not twice as much fuel, but 10 or even 20 times more. It is analogous to attempting to ascend an endlessly steepening hill. Each step forward demands disproportionately more strength than the last, until eventually movement becomes impossible. Even the mighty Saturn V, which ferried the Apollo astronauts to the moon, was predominantly fuel. More than 90% of its total mass at launch, some 2,700 tons of propellant, was consumed simply to propel a small capsule and a handful of individuals beyond Earth's gravitational embrace. What ultimately reached space was a mere fraction of what began the epic journey. The same fundamental principle holds true for every rocket ever constructed. The payload, the actual object one wishes to deliver, invariably constitutes the smallest component of the entire system. This inherent imbalance is what fundamentally anchors us to our cosmic home. Chemical rockets can transport us to orbit, to the moon, and perhaps to Mars. But the stars represent an entirely different magnitude of challenge. Imagine attempting to construct a chemical rocket colossal enough to achieve even 1/10 the speed of light. The quantity of fuel demanded would be utterly absurd, a mass greater than that of our entire planet. The rocket equation unequivocally demonstrates this. The faster one desires to travel, the more devastating the mathematical implications become. It is not merely impractical, it is physically impossible with current chemical propulsion technology. At a certain threshold, adding more fuel contributes nothing but additional weight, eventually causing the rocket to collapse under its own prohibitive burden. This is precisely why space agencies and physicists frequently discuss propulsion ceilings. Chemical rockets are already operating near their fundamental limits. Every new design, whether it is the Space Launch System Falcon Heavy or Starship, employs variations of the same ancient principle: controlled explosions expelling exhaust downward. While technological advancements have indeed rendered them more reusable, more cost-effective or safer, in terms of fundamental velocity, they remain bound by the very same chemistry that powered the rudimentary rockets of the early 20th century. The improvements are predominantly logistical, not fundamental. We are in essence brushing against the absolute pinnacle of what this method can achieve. It is a humbling realization how infinitesimally narrow that limit is when juxtaposed against the breathtaking scale of space itself. Chemical rockets can convey us from Earth to the Moon in a matter of days, to Mars in several months, and to the outer planets in years. But beyond that, their utility rapidly diminishes. Beyond the orbit of Neptune, their tiny reserves of thrust can barely make a discernible difference. Spacecraft like Voyager and New Horizons predominantly rely on gravitational assists, cosmic slingshots around massive planets, to acquire the additional speed they require. Yet even this clever stratagem offers only limited assistance. Once they have definitively departed the solar system, they are consigned to coast indefinitely, slowly bleeding energy into the eternal dark. The fundamental reason for this inefficiency lies in the intrinsic mechanisms of energy storage and release. In chemical rockets, energy is liberated by the rearrangement of atomic bonds. However, these bonds hold only a finite, limited amount of power. Nuclear reactions, by stark contrast, release millions of times more energy per unit of mass. This profound difference is precisely why the next generation of theoretical propulsion concepts, fusion or fission, is universally regarded as the only viable path forward for interstellar travel. Yet even these methods are fraught with immense technical challenges. For the present, chemistry remains our indispensable workhorse, a technology both intimately familiar and frustratingly weak. And even if we could somehow push a chemical rocket to greater extremes, we would rapidly encounter yet another insurmountable barrier: heat. The faster fuel is combusted, the hotter the engine becomes. At a certain point, no known material can withstand the exorbitant temperatures. Even advanced alloys melt, vaporize, or crack under the extreme thermal stress. Engineers can devise sophisticated cooling systems, but these systems inevitably add mass, which in turn demands more fuel, which then generates even more heat. It is an endless self-defeating cycle of trade-offs, one that invariably culminates at the same fundamental barrier. This is the unyielding hard ceiling of rocket physics. Every conceivable form of propulsion fundamentally depends on the energy intrinsically locked within matter, and chemical energy is simply insufficient for interstellar scales. The velocities required to traverse interstellar distances are so colossal that our most powerful rockets are akin to flickering candles attempting to illuminate the night sky. They glow brightly for a fleeting moment, rapidly consume their fuel, and then inevitably fade into insignificance. When the first pioneering astronauts ascended into their cramped capsules, they were ensconced atop machines that represented the absolute pinnacle of what chemistry could achieve. 60 years later, despite monumental advancements in materials science, computing power, and design methodologies, we still rely on precisely the same fundamental process. There is something both inherently heroic and tragically ironic about this reality. Heroic because we have attained incredible heights with demonstrably limited tools. Tragic because those very tools have now propelled us as far as their intrinsic limitations allow. The dream of fusion drives, the profound concept of a fusion drive, sprang from the very same human instinct that first gave birth to rockets, the innate desire to harness the most fundamental forces of nature for the purpose of motion. If the raw power of fire could lift us from Earth's surface, then perhaps the very energy that ignites the stars themselves could convey us across the cosmic void. Nuclear fusion is the precise process that fuels our sun, converting hydrogen into helium and unleashing colossal amounts of energy in the process. A fusion engine would aim to replicate this stellar process, but under meticulous control, capturing that immense power and directing it as thrust. In theoretical terms, such a breakthrough could render interstellar travel plausible within a single human lifetime. In practical terms, however, it remains an elusive dream confined behind towering walls of physics and engineering knowledge that we have yet to scale. The concept first garnered serious scientific attention in the 1970s with a groundbreaking project known as Daedalus. Undertaken by the British Interplanetary Society, it posed a singular question: could humanity, utilising technology projected to be available within a century, construct a spacecraft capable of reaching another star? The team selected Barnard's star, a red dwarf, approximately 6 light-years distant as their target. The objective was not to transport human beings, but a robotic probe, a vessel capable of traversing that unimaginable distance within 50 years. Project Daedalus envisioned a colossal ship nearly 200 meters in length, powered by meticulously controlled nuclear fusion. Its engines would consume pellets of deuterium and helium-3 light isotopes of hydrogen that release immense quantities of energy upon fusion. To initiate these reactions, the ship would employ powerful electron beams triggering miniature thermonuclear explosions within a magnetically contained chamber. Each tiny blast would exert force against a massive magnetic nozzle, thereby generating thrust. Over a projected 4-year period, the ship would accelerate to an astonishing 12% of the speed of light, over 36,000 kilometers per second, a velocity sufficient to cross interstellar space in half a century. The numerical requirements were staggering. To fuel such an epic journey, the spacecraft would necessitate approximately 50,000 tons of fusion fuel, all of it hypothesized to be mined from the atmospheres of gas giants like Jupiter. The entire colossal vessel would have to be assembled in orbit far from Earth, as no planet could safely accommodate a rocket engine that effectively detonated small nuclear explosions for propulsion. The sheer cost and complexity of this endeavour were beyond anything achievable then, and indeed remain so even now. However, the underlying physics were fundamentally sound. In principle, a fusion engine could work. The overwhelming challenge lay not in the mathematical theory, but in the practical construction of a system that could endure its own immense power. This is precisely where the dream has remained stubbornly stalled ever since. Fusion itself is inherently difficult. Containing it is exponentially harder. For decades, scientists on Earth have relentlessly endeavoured to recreate the sun's processes within terrestrial reactors, not for space travel, but for generating electricity. They have constructed intricate magnetic confinement machines like the tokamak and stellarator, designed to suspend superheated plasma in place using immense magnetic fields. They have also utilised powerful lasers to compress tiny fuel pellets in advanced laboratories, such as the National Ignition Facility. Real progress has been made, but it is agonisingly slow. Achieving ignition, the critical point where fusion reactions release more energy than they consume, has only been accomplished for fractions of a second and under highly delicate laboratory conditions. Transforming that fleeting success into a steady, controlled and sufficiently powerful thrust for propulsion represents an entirely different order of magnitude leap. A functional fusion drive would not merely need to initiate fusion, it would need to sustain it thousands of times per second in perfect synchronicity, all while enduring the immense heat and radiation of its own exhaust. The interior walls of the combustion chamber would be constantly bombarded by energetic particles hotter than the sun's core. The magnetic fields essential for containing the plasma would have to be extraordinarily stable and precise. Any minute disturbance could catastrophically destroy the entire system, and all of this would have to occur within a spacecraft light enough to accelerate to a significant fraction of light speed. It is not theoretically impossible, but in practice it represents a colossal mountain of interconnected challenges stacked one upon another. Yet fusion persistently occupies a central place in the human imagination as the logical next monumental step. Modern iterations of Project Daedalus have been proposed, most notably Project Icarus in the 2010s, a collaborative effort by engineers and physicists to re-evaluate the concept using contemporary tools and knowledge. The fundamental goal remains unchanged: to design a self-sustaining fusion-powered probe capable of reaching another star within a century. Icarus incorporates numerous refinements, improved magnetic confinement systems, lighter and more resilient materials, and more sophisticated onboard artificial intelligence. However, the inherent scale of the challenge remains enormous. The difficulty extends beyond mere construction. It encompasses sustaining continuous operation over decades without maintenance, all while traversing interstellar dust that could erode its hull grain by grain at relativistic speeds. What makes fusion so irresistibly alluring is its extraordinary energy density. A fusion reaction unleashes millions of times more energy per kilogram than conventional chemical fuel. With that kind of unprecedented power, a spacecraft could conceivably accelerate for months or even years rather than mere minutes. It could maintain its relentless push until it attained a significant fraction of the speed of light. Such a journey to Proxima Centauri could theoretically be accomplished in just a few decades, fast enough to envision a ship launched by one generation and met by the next. While still slow in cosmic terms, it would finally bring the stars within the outer bounds of human patience. But the inherent elegance of this idea conceals its profound fragility. The fusion process itself demands a level of precision that no spacecraft has ever been required to maintain. Even our most advanced experimental reactors on Earth are colossal, delicate machines, reliant on teams of highly specialized scientists and constant calibration. A fusion drive, conversely, would need to operate autonomously in the depths of space for decades, managing immense forces without the possibility of repair. It would need to store and meticulously feed thousands of tons of fuel pellets into its chamber with impeccable timing, all while simultaneously enduring micrometeorite impacts and intense radiation. It is not merely a question of making fusion work. It is about making it work flawlessly in the harshest imaginable environment, far from human intervention. Still, research persists in various promising avenues. Advances in superconductors and refined magnetic field designs have rendered compact reactors more plausible. Some laboratories are actively exploring novel approaches such as magnetized target fusion, which cleverly blends the principles of inertial and magnetic confinement. These cutting-edge concepts, if successfully miniaturized, might one day serve as the foundational bedrock for a fusion engine. Others envision hybrid systems where powerful lasers ignite micropulses of fusion, with each precisely controlled pulse propelling the ship forward like a series of miniature orchestrated explosions. This remains speculative science, yet it is not without considerable merit. The very same technological tools that could one day power our cities might also in time propel our ships to the distant stars. Yet it is crucial to reiterate that no fusion device has yet achieved continuous power output even on Earth. What we can currently accomplish in a laboratory for a few fleeting seconds, we are still decades away from sustaining. Transforming that into a practical propulsion system, something that must function reliably for years on end, pushes that timeline even further into the future. The dream of fusion drives belongs firmly to the borderland between ambitious engineering and pure imagination. It paints a compelling picture of what might be possible if humanity successfully resolves some of its most intractable scientific problems. But for now it remains an elegant idea more than a concrete plan. Every generation has its seemingly unreachable dream, and fusion is undeniably ours. It sits perpetually on the horizon of our technological capabilities, always just beyond our immediate grasp, yet radiating brightly enough to continually draw us forward. Beaming a ship across the stars, imagine a spacecraft devoid of an engine, without fuel and entirely uncrewed. Just a thin, shimmering sail propelled by light itself. Instead of carrying its own bulky propulsion system, this vessel would ride upon energy projected from its homeworld, driven by the relentless subtle pressure of light. It sounds like the purest science fiction, and in many respects it remains so. Yet the fundamental physics underpinning it are undeniably real. This is the ambitious vision of breakthrough Starshot, an audacious attempt to transform light, the universe's most constant and swift traveller, into a viable means of interstellar flight. The concept begins with a simple, elegant truth light carries momentum. Although individual photons possess no mass, they nonetheless exert a minuscule, yet measurable push when they strike a reflective surface. On Earth, this force is far too weak to noticeably move anything. But in the vacuum of space devoid of air resistance, even the faintest continuous pressure can cumulatively build astonishing speed over time. If a consistent stream of light is directed onto a mirror, that mirror will eventually accelerate. Scientists have conceptualized harnessing sunlight in this manner for decades. The idea of a solar sail, propelled by photons from our sun, has appeared extensively in literature films and even in real-world missions such as Japan's Icaros probe and NASA's NEA Scout. However, direct sunlight is inherently weak. Its intensity diminishes rapidly with distance. To embark on a journey to another star, one would necessitate something far more potent, an artificial sun meticulously crafted from lasers. This is precisely where Breakthrough Starshot intervenes. Announced in 2016 and championed by the late physicist Stephen Hawking and investor Yuri Milner, the project proposes the construction of a gargantuan array of ground-based lasers, potentially thousands of them, working in perfect synchronized harmony to generate a beam of unprecedented power. This concentrated beam would then be focused onto a tiny spacecraft attached to a reflective sail, only a few meters wide yet weighing just a few grams. The overarching objective is to accelerate that sail to an astounding 20% of the speed of light, approximately 60,000 kilometers per second, in a matter of mere minutes. At such incredible velocity, it could theoretically reach Proxima Centauri in slightly over 20 years. It is difficult to overstate the radical nature of this concept. Traditional spacecraft are inherently heavy, burdened with fuel and numerous instruments. Starshot completely inverts this logic. The probe itself would be no larger than a microchip carrying miniature cameras, sensors and communication systems. The sail would be an ultra-thin, hyper-reflective sheet, fabricated from advanced materials like graphene or specialized metamaterials. Materials light enough to withstand the immense heat of the laser array and smooth enough to maintain stability under extreme acceleration. In essence, the ship would not propel itself. It would be thrown across space by the light from Earth. Once the laser beam ceased, it would then coast for decades through the profound dark, carrying humanity's technological presence into another star system. However, the elegant simplicity of the concept masks monumental difficulties. The first and most conspicuous challenge is precision focus. To accelerate a sail to a fraction of light speed, the laser beam must remain flawlessly aligned with it throughout the entire boost phase. Several critical minutes, even as the sail rapidly recedes thousands of kilometers away from Earth. Any minute wobble or misalignment would cause the beam to either miss the sail entirely or worse, burn through its delicate structure. At such extreme velocities, even a tiny variation in the reflective surface could induce uncontrollable spin. The engineering precision demanded is utterly beyond anything humanity has ever attempted. The laser array would need to coordinate its thousands of individual lasers with millisecond timing dynamically adjusting for atmospheric distortion, Earth's rotation, and thermal expansion. Then there is the formidable problem of energy. To achieve 20% of light speed, the laser array would need to output approximately 100 gigawatts of power, roughly equivalent to the entire electrical capacity of a large industrialized nation, sustained for several minutes. This represents an extraordinary burst of concentrated energy, and it must be channeled into a beam that traverses Earth's atmosphere without significant scattering. Even the construction of such a colossal array presents a staggering challenge. It would need to span several square kilometers and operate with absolute perfect synchronization. And once the sail departs the beam, it is irrevocably gone. There is no slowing down, no course correction, no return journey. Assuming these monumental obstacles are somehow overcome, the journey itself remains fraught with peril. Even a single grain of dust no larger than a speck of sand could unleash enough energy upon impact at relativistic speeds to vaporize the minuscule spacecraft. Engineers have proposed various protective strategies such as employing forward shields or perhaps orienting the sail edge-on during flight, but no proven solution currently exists. Every kilometer traversed through interstellar space would be a silent, high-stakes gamble against the unknown. Communication presents another major hurdle. A probe weighing only a few grams cannot carry a large antenna or a powerful transmitter. When it eventually reaches Proxima Centauri, 4.2 light-years distant, its faint signal would require over 4 years to return to Earth, and would be so attenuated that even our largest radio telescopes might struggle to detect it. Engineers envision the sail itself potentially serving as a transmitter, beaming data back using a tiny onboard laser. But this necessitates pinpoint aiming accuracy across trillions of kilometers. The challenge is not merely to reach the stars, but to transmit a coherent whisper back from them. Despite all these profound difficulties, the allure of the breakthrough starshot concept is undeniable. It represents a truly revolutionary approach to space travel, one that fundamentally does not rely on the spacecraft carrying its own fuel, but rather on external power meticulously projected from home. If perfected, the same methodology could be adapted for slower, larger probes destined for the outer planets, or even for dispatching small payloads to distant corners of our solar system at unprecedented speeds. It is an approach that could over time transform space exploration from a series of rare, immensely expensive missions into something more akin to a widespread network. Tiny mass-produced scouts riding beams of light to meticulously map the universe. In a profound sense, Breakthrough Starshot is as much a philosophical paradigm as it is a technological proposition. It acknowledges the inherent limitations of conventional rockets, and boldly embraces an entirely different principle, the radical separation of the energy source from the spacecraft itself. Instead of carrying the immense burden of power with us, we send it after us. This is what renders the concept so elegantly efficient. It transforms space travel into something resembling wireless energy transfer on a cosmic scale. The ship becomes featherlight, Earth becomes the engine. But there is also an inherent fragility within that grand vision. The entire system is predicated upon a single, unbroken connection, the laser beam between the ground array and the sail. If that connection falters, the mission fails. Once the beam dissipates, the probe transforms into a drifting speck, unpowered and unprotected, forever coasting through the profound darkness. It serves as a stark reminder that even our most advanced, seemingly futuristic ideas remain ultimately bound by the immutable realities of physics and the crushing immensity of distance. The further we dare to dream, the more tenuous and fragile our reach becomes. And yet the sheer idea that a human-made object no larger than a thumbnail could successfully traverse the vast chasm between stars is a potent symbol of both our intrinsic limits and our boundless courage. It communicates something profound about the extent to which we are willing to push the boundaries of the possible. The very first Starshot probe, if it is ever successfully launched, may not survive its perilous journey. It may be vaporized by an unseen dust particle, or its faint signal may never successfully reach us. But the audacious attempt itself would unequivocally mark a monumental turning point. For now, the technology remains on drawing boards and confined to computer simulations. But if it ever works, it would signify that humanity has at long last discovered a way to touch another star without expending a single atom of onboard fuel. When atoms become the enemy, space often appears empty, a pristine vacuum. But it is not. Between the stars stretches a thin, pervasive haze of matter, scattered hydrogen atoms, microscopic dust particles, and occasional clusters of heavier elements, all drifting like invisible ghosts. It is so incredibly sparse that on average only a few atoms occupy each cubic centimetre. To human senses it would register as absolute nothingness. But when one moves fast enough, even nothing can become lethally dangerous. For a ship travelling at velocities approaching the speed of light, those widely dispersed atoms transmute into an incessant storm of invisible projectiles. When an object accelerates close to the speed of light, its kinetic energy increases dramatically. Even a minuscule object can carry an immense destructive force. A single hydrogen atom striking a spacecraft at 1/10, the speed of light impacts with the energy equivalent to hard radiation. Multiply that by billions upon billions, and the seemingly empty space between stars becomes a ceaseless barrage of invisible fire. The faster a ship accelerates, the worse this problem becomes. At 10% of light speed, the impact of a dust grain no larger than a sand particle could unleash as much energy as a small explosive device. At half the speed of light, it would be akin to being struck by a bullet moving faster than anything on Earth. At 99% of light speed, a mere speck of dust could tear through reinforced metal like a cannon shell. For a starship, this transforms interstellar space into something resembling a deadly minefield. The individual atoms are far too small to see or actively avoid, and they move relative to the ship at truly incredible speeds. Even the thinnest components of interstellar gas, which are utterly harmless to slower spacecraft, become superheated plasma waves capable of stripping atoms directly off the hull. The faster one travels, the denser the interstellar medium appears. Not because there are physically more atoms, but because relativistic effects compress the particles ahead of the ship. The spacecraft would perceive them as a fierce continuous wind, a radiation storm composed of matter itself. To survive such a perilous journey, any interstellar craft would need to be transformed into an impenetrable fortress. Engineers who meticulously study hypothetical relativistic flight envision ships, fortified with immense shielding at their bows composed of thick layered materials specifically designed to absorb or deflect these high-speed impacts. The bow itself might be shaped like a long, tapering cone, effectively spreading impact energy away from the main structural integrity. Some designs even propose employing magnetic fields powerful enough to push charged particles aside before they can strike the hull. However, each of these proposed solutions introduces new, formidable problems. The necessary shields would add prohibitive weight, and every extra kilogram makes achieving significant acceleration exponentially harder. The magnetic fields would demand enormous power, and they might prove ineffective against neutral atoms or larger dust grains. Every form of protection adds yet another layer of engineering challenge. The paradox is profoundly cruel. To shorten the trip, a ship must achieve extreme velocity. To survive travelling at extreme velocity, it must carry massive protection that makes it heavy, which in turn inevitably slows it down again. There is no simple, elegant balance point. The faster one attempts to travel, the more the universe itself appears to actively resist, even if one were to imagine perfect shielding, something capable of completely absorbing or instantly vaporizing dust upon impact. The sheer heat generated would be catastrophic. The ceaseless rain of particles at near-light speeds would generate immense friction-accumulating energy, faster than any conceivable cooling system could manage. The forward surfaces of the ship could glow incandescently white-hot, even within the frigid dark of interstellar space. Scientists have diligently attempted to estimate the practical implications of this. For instance, a ship travelling at just 30% of the speed of light would encounter approximately 1 trillion particles per square metre every single second. While each individual particle might carry only a minuscule fraction of a joule collectively, they would deposit immense quantities of energy. This constant bombardment would slowly, relentlessly erode the hull, generating secondary radiation that could fry delicate electronics or irrevocably damage onboard systems. Over extended periods, even the most advanced materials would inevitably crumble. The faster the ship travels, the more violent and hostile the environment becomes, until the void itself transforms into a lethal adversary. It is easy to forget how profoundly hostile interstellar space truly is, precisely because we conceptualize it as endless emptiness. But that very emptiness conceals immense energy. It harbors radiation from distant stars' cosmic rays that have traversed millions of years and minute dust grains shed by dying suns. Every single one of those particles, utterly harmless to a stationary observer, becomes a deadly weapon when impacted at relativistic speeds. It is akin to driving through a fine mist that instantaneously solidifies into steel needles the moment one accelerates. One theoretical solution, at least in principle, would be to simply travel slower. If the ship's velocity were limited to just a few percent of the speed of light, the impacts would become less catastrophic. But that choice inevitably means the journey would extend for far longer, centuries, even millennia. A mission to Proxima Centauri at 1% of light speed would require over 400 years. The probes we launch today would be long defunct by then. Human beings, if they ever rode such a vessel, would never live to witness its ultimate destination. And so we find ourselves ensnared in a cruel dilemma between speed and survival. Travel too fast and the ship is utterly destroyed. Travel too slow and the mission loses all practical meaning. The universe, it seems, meticulously guards its distances with invisible, unyielding walls. There is also the ever-present problem of cosmic rays. Even today, astronauts aboard the International Space Station experience doses of cosmic radiation hundreds of times higher than on Earth's surface. For a ship moving at a significant fraction of light speed, those rays would appear even more intensely concentrated due to relativistic effects. The forward direction of travel would compress the incoming radiation into a narrow, deadly beam. The ship would essentially be flying directly into a constant, overwhelming storm of hard radiation, potent enough to damage sophisticated electronics, and if crewed to kill its human passengers without truly extraordinary shielding. Some researchers have ingeniously suggested utilising the very atoms ahead as part of the solution, proposing the creation of a magnetic bow wave that ionises the incoming gas before it impacts, deflecting it sideways. It is an elegant concept, but it demands magnetic fields far stronger than anything we can currently generate. The ship would require superconducting magnets the size of entire buildings, cooled to near absolute zero, operating flawlessly for decades. Even then, neutral dust grains would still remain an intractable problem. The sobering truth is that we have only just begun to grasp the true complexity of this multi-layered problem. The interstellar medium is not uniform. It is filled with patches of denser gas turbulent shock fronts from ancient supernovae and vast clouds of dust spanning hundreds of light years. A ship could traverse regions of relative safety, then suddenly plunge into a zone thick with microscopic debris. Each grain it strikes would subtly erode its surface a little more. Over decades, that relentless erosion could eat through meters of protective shielding. What is most unsettling is the utterly invisible nature of this threat. One cannot see a hydrogen atom approaching. One cannot chart every single dust grain between here and Proxima Centauri. The interstellar medium is simply too vast, too tenuous, too randomly distributed. Even if such a map were possible, the ship itself would be moving far too fast to react in time. There would be no dodging, no shielding robust enough to last indefinitely. The success of the journey would depend entirely on how accurately we could predict what lies ahead, and how resiliently our materials could endure what they cannot avoid. Navigating through nothing, once a spacecraft departs the gravitational embrace of our solar system, it leaves behind the last familiar lights of home, the sun, the planets, the subtle pull of our magnetic field. Beyond that crucial boundary, there are no readily discernible guideposts, no recognisable landmarks, and no compass that functions reliably. A ship venturing between the stars must navigate through an abyss of pure darkness, enveloped by an endless tapestry of distant points of light that all appear equally remote. It is a journey through profound nothingness where even a fraction of a degree of error in trajectory can result in drifting irretrievably off course forever. On Earth, navigation is deceptively simple due to the abundance of stable reference points. We can follow coastlines, track familiar stars, or utilise magnetic compasses to orient ourselves. Even in near-Earth space, satellites rely on the Sun and Earth's magnetic field for precise positioning. But as a spacecraft journeys outward, these familiar tools progressively fade. The Sun diminishes into a faint star among billions. Its gravitational influence weakens, its light grows dim, and its magnetic field effectively dissolves into the background noise of the cosmos. The familiar grid that has guided every spacecraft thus far simply vanishes. What remains is an immense ocean of emptiness, and determining direction within it becomes one of the most formidable problems in interstellar flight. A ship departing the solar system would need to rely almost entirely on the stars themselves. This concept is not entirely novel. Ancient mariners once utilised constellations to navigate across Earth's oceans. But for a starship, the challenge is magnified to an extreme degree. The stars it observes are not truly fixed. They shift slowly over vast timescales, and their apparent positions constantly change as the ship itself moves at incredibly high speeds. Light from those stars requires years to reach the ship, meaning its map of the sky is inherently out of date. The faster it travels, the less accurate its celestial picture becomes. Even the most advanced navigation system must continuously update its perception of the cosmos, and it must do so without any external assistance. One proposed method involves pulsars, rapidly spinning neutron stars that emit highly collimated beams of radio waves in incredibly precise repeating patterns. Each pulsar possesses a unique rhythm, akin to a cosmic clock. By meticulously measuring the arrival times of signals from several known pulsars, a spacecraft could triangulate its position with remarkable accuracy, much like how GPS functions on Earth. This technique, known as XNav X-ray navigation, has already been successfully tested in orbit around Earth with promising results. In theory, a network of pulsars could serve as a natural interstellar GPS, providing a ship with precise coordinates based on the meticulous timing of their flashes. But even this elegant system faces inherent limitations. The signals themselves are incredibly faint and easily overwhelmed by cosmic background noise. The detectors must be extraordinarily sensitive, meticulously cooled and rigorously shielded from interference. A ship travelling at relativistic speeds would also have to meticulously account for time dilation, the strange warping of time that accompanies movement near the speed of light, which would subtly shift the timing of those pulsar flashes, making calculations far more complex. If pulsars can provide position, the subsequent critical question is orientation, knowing precisely which way the ship is pointed. In deep space, a spacecraft's attitude or rotation cannot be measured against any nearby object. There is no absolute up or down, no discernible horizon. Engineers must rely on sophisticated gyroscopes and star trackers, instruments that sense rotation and compare observed star patterns to an onboard pre-stored celestial map. But even these highly precise systems inevitably drift over time. A gyroscope, no matter how accurate, will accumulate tiny errors. Over months or years, those errors compound until the ship's computer no longer precisely knows its orientation. On interstellar timescales, even a single degree of error could send a probe veering thousands of kilometers off target. Correcting that drift would necessitate continuous recalibration, meticulously comparing the apparent positions of distant stars and galaxies to what the ship expects to see, a task demanding perfect timing and extraordinary computational precision. Communication further complicates this delicate balancing act. To communicate effectively with Earth, a spacecraft must precisely point its antenna directly towards home. A radio dish just a few meters wide, situated billions of kilometers distant, must maintain alignment with incredible precision. If the beam drifts even slightly, the signal will completely miss Earth. And as distance increases, the target aperture shrinks. For interstellar missions, this implies that even tiny course corrections must be executed with extreme care, utilizing thrusters that produce almost no unwanted rotation or wobble. Every pulse of a maneuvering jet must be meticulously planned, exhaustively modelled, and rigorously verified before being fired. A mistake made at 1% of light speed could never be undone. Without the sun's encompassing gravity to anchor it, a spacecraft in interstellar space also confronts another invisible threat drift. Space is not perfectly smooth. It contains faint gravitational tides exerted by nearby stars and tenuous clouds of gas. Over extended timescales, these minute forces can subtly nudge a ship's trajectory, incrementally altering its path by imperceptible degrees. If a probe were aimed with absolute precision at another star, those small, persistent tugs could subtly bend its flight path sufficiently to cause it to miss its target entirely. Correcting for this demands a continuous real-time awareness of its exact position. But the farther a ship travels, the more challenging it becomes to measure that position with requisite accuracy. By the time Earth receives a signal indicating the ship is slightly off course, the vessel will already be light years farther along its journey. This reality underscores why interstellar navigation fundamentally demands autonomy. A probe cannot afford to await instructions from home. Lightspeed communication is simply too slow. By the time engineers on Earth could react to a detected problem, the mission would likely already be irretrievably lost. The spacecraft must possess the inherent capability to sense, compute, and adjust its course entirely by itself. It must carry an internal dynamic model of the galaxy, meticulously measure its own motion, and correct its flight path without any human intervention. Such a level of artificial intelligence necessitates software capable of interpreting faint starlight, precisely timing pulsar flashes, and executing constant self-checks, all while enduring the relentless bombardment of cosmic radiation and decades of profound isolation. Some engineers envision ships equipped with arrays of small optical telescopes continuously scanning the celestial sphere. The onboard computer could meticulously compare the observed star field to known catalogues, much like a sailor consulting a map. By calculating the subtle parallax shifts, how stars appear to move relative to each other as the ship changes position, it could estimate its speed and direction. However, these shifts are incredibly minute. Even for a ship travelling at 1/10th, the speed of light, it might take years before any measurable change in the starfield becomes apparent. During that extended period, the ship would have to place absolute trust in its instruments, continually adjusting its path based on sophisticated predictions and simulations rather than immediate clear measurements. The same profound difficulty applies to executing turns or deceleration. A ship that traverses light years must plan its maneuvers decades, even centuries in advance. Every change in orientation, every correction burn consumes precious energy and alters the intricate geometry of the onboard navigation system. Thrusters designed for stability must fire with perfect symmetry, or the ship could initiate an uncontrollable spin. Without external reference, detecting and arresting such a spin becomes nearly impossible. The craft would have to infer the spin by observing stars sliding across its cameras and painstakingly calculating the motion backward, a form of celestial dead reckoning that depends entirely on the flawless aging of its instruments. In human terms, this is akin to sailing across an ocean so vast that the stars above are one's only compass, except the stars themselves are subtly shifting. The ocean is invisible, and every cosmic gust of wind might imperceptibly alter one's heading. There is no visual horizon for correction, no immediate sense of speed, no tactile resistance. The ship could be drifting fundamentally off course for years before it even registers the deviation. To maintain alignment with its target star, the navigation system must uphold an accuracy down to fractions of a microdegree, a feat no existing spacecraft has ever achieved over such extended timescales. Even the seemingly simple act of measuring time becomes profoundly challenging. Onboard atomic clocks must maintain their stability for decades or more, entirely unaffected by pervasive radiation or extreme temperature fluctuations. A single timing error could skew pulsar calculations, leading to critical navigational drift. Engineers discuss the imperative need for self-healing systems, networks of redundant clocks and sensors that constantly cross-check each other autonomously, detecting flaws before they escalate into catastrophic failures. The craft must not only know where it is, but know that it knows, a strange recursive awareness that might one day define the first truly intelligent probes. Then there is communication itself. The Deep Space Network already operates at the very limits of sensitivity. Engineers envision utilizing laser communication, instead focusing an incredibly narrow beam of light directly at Earth. But this renders alignment even more critical. The laser must remain locked onto its target with near-perfect accuracy, despite the ship's constant motion and subtle vibrations. Navigating through nothingness, therefore, is not merely a technical challenge. It probes a deeper question: how do we find our way when no markers remain to guide us? When even light and time become unreliable companions, a ship that journeys between the stars must do more than simply move. It must perceive. It must transform the emptiness itself into a reference, meticulously reading the faint whispers of radiation and gravity as subtle clues to its precise position. The deceleration problem. Getting a spacecraft up to incredible speed is remarkably only half the battle. The harder part, the crucial phase often quietly omitted from grand interstellar mission concepts, is the intricate challenge of slowing down again. Once a probe is hurtling between the stars, it possesses nothing to push against. No atmosphere to break through, no convenient planet to orbit until its journey is concluded. It will continue moving indefinitely unless an external force intervenes to halt it. In the profound vacuum of space motion is in essence eternal. This fundamental principle is what renders the deceleration problem so acutely difficult. If a probe were launched towards Proxima Centauri and somehow accelerated to a fraction of light speed, it would lack any inherent means to slow down. Without an external braking force and devoid of onboard fuel to burn, it would shoot straight past the target system, vanishing irrevocably into the vast darkness beyond. The faster it travels, the more acute this problem becomes. At 10% of light speed, the probe would traverse the entire Proxima system in a mere matter of hours. It could in principle gather some data as it flew by, but it would never be able to linger for a closer examination, never enter orbit, never transmit detailed images from within the system. It would be a fleeting blur, a silent visitor that perceives everything once and never returns. This stark reality fundamentally alters how we must conceptualize interstellar exploration. Speed alone is insufficient. The critical ability to stop, or at least significantly decelerate, is what transforms a simple flyby into a genuine encounter. Without the capacity for deceleration, all we could ever achieve is a momentary glance at the stars as we rush past them. However, slowing down after accelerating to such enormous velocities demands as much or often more energy than the initial journey itself. In spaceflight, every maneuver incurs an energy cost, and that energy must originate from somewhere. On Earth, we can conveniently rely on friction, atmospheric drag, and gravitational fields to assist in deceleration. Space, however, offers none of that mercy. To decelerate purely through propulsion, a probe must carry enough fuel to precisely cancel its own colossal momentum. The faster it travelled, the more fuel it would require to stop, but every additional unit of fuel adds mass, and the heavier the probe, the more fuel it needs simply to move at all. This creates a relentless self-defeating loop, the rocket equation, in its purest, most unforgiving manifestation. A probe designed to reach even 1/10 of light speed would necessitate thousands of times its own mass in fuel just for acceleration, and an equivalent amount again purely for deceleration. This is precisely why most interstellar mission designs quietly circumvent the deceleration phase. The Breakthrough Starshot concept probes, for instance, are explicitly designed without a braking system. Upon reaching Proxima Centauri, they are projected to flash through the system in mere seconds. Their miniature onboard cameras would be forced to record everything in an instant, transmitting whatever minuscule data they can before the signal irrevocably fades. The journey itself would span over 20 years, yet the actual encounter would last less than the blink of an eye. The cherished dream of entering orbit, meticulously studying Proxima B's surface, or deploying instruments onto its soil. All of this remains currently impossible with prevailing technological paradigms. Some researchers have proposed ingenious solutions. One idea involves leveraging the destination star's own light as a brake. Just as a solar sail can harness photons to accelerate, it could theoretically be deployed in reverse orienting the sail to face the oncoming starlight, allowing the radiation pressure to gradually decelerate the ship. In theory, this could work, but only if the sail is gargantuan, extraordinarily reflective and virtually indestructible. Even then, the force exerted by starlight is minuscule. It would require years to bleed off significant velocity, and the probe would have to pass incredibly close to the star to gather sufficient light pressure. The intense heat and radiation in such proximity would likely destroy the delicate sail long before the ship could effectively stop. Another intriguing proposal is to utilize magnetic fields as a type of cosmic parachute. Space is pervaded by sparse particles and the diffuse magnetic fields of the interstellar medium. A probe could deploy an immense magnetic field ahead of it, effectively sweeping up charged particles and leveraging their inherent resistance to slow down. This is known as a magnetic sail, or mag sail. The concept is elegantly simple, utilizing the tenuous plasma of space as a natural brake. But the physics involved are brutal. The density of interstellar matter is so exceptionally low that even a monumentally powerful magnetic field would require decades to perceptibly slow a ship travelling at high speeds. The magsail itself would need to be colossal, spanning kilometres, and its intricate structure would have to survive relentless collisions with high-energy particles at relativistic velocities. Like so many ambitious ideas in interstellar engineering, it works beautifully on paper, but consistently collapses under real-world conditions. Some scientists even suggest employing the gravitational pull of the destination star as a brake, executing a close pass to trade speed for a modified trajectory. However, such a gravity assist primarily alters direction. It does not inherently reduce overall velocity, unless the ship can also push against another object such as a planetary atmosphere. And in an alien star system, there are no guarantees of planets or atmospheres suitable for such a manoeuvre. Even if they existed, the precision required to achieve such a target at a fraction of light speed is almost unimaginable. A small navigation error made years earlier would send the probe hurtling past the system entirely. In every conceivable scenario, the same immutable truth emerges: slowing down is inherently harder than speeding up. Acceleration can be achieved through various means, but deceleration invariably demands interaction with something external. And in the profound emptiness of interstellar space, there is almost nothing available for interaction. Every kilogram of propellant that could be utilised for deceleration must be carried from the very outset of the mission. It is a fundamental trap woven into the very fabric of physics. The deceleration problem also critically shapes what kind of missions are even remotely possible. A human expedition, for example, would be utterly impossible without a viable means to stop safely. Even at modest fractions of light speed, the energy required to decelerate a crewed ship would be equivalent to that of several nuclear arsenals. There is no known material that could withstand the generated heat or the immense stresses of braking under those conditions, and if the ship was simply to coast past its destination, there would be no second chance. The crew would continue drifting through space forever irrevocably, unable to turn back. One far future concept to address this problem stems from the notion of deploying twin laser systems, one on Earth, to initiate acceleration, and another strategically positioned within the destination system to facilitate deceleration. The ship would approach, precisely turn its sail around, and allow the incoming light from the distant laser to push against it, gradually bringing it to a halt. It is a symmetrical and elegant concept, but it fundamentally assumes something crucial: that a laser system already exists at the target. In other words, we could only decelerate if someone or something were already there to assist us. For now, that remains firmly within the realm of science fiction, though it hints at the extraordinary scale of cooperation that true interstellar travel would ultimately demand. The more realistic conclusion is that the very first journeys to the stars will not involve stopping. They will be fleeting glimpses, not extended visits. Probes will rush through alien systems, meticulously recording as much data as possible before vanishing into the void beyond. It is the same fundamental approach that Voyager utilised when it passed Jupiter and Saturn. Moments of breathtaking discovery achieved through brief, exhilarating flybys. The very act of reaching another star, even without the capacity to stop, would still constitute an unparalleled triumph. It would signify that something constructed by human hands successfully traversed the immense gulf of interstellar space. Yet the deceleration problem serves as a poignant reminder that the universe does not readily grant such achievements. Momentum is both our greatest ally and our most formidable adversary. It propels us forward, yet it also traps us in perpetual motion. Once one is moving fast enough to journey between stars, stopping becomes the single hardest endeavour in the entire cosmos. Once such a journey begins, one can never truly turn back. The ship ultimately becomes an indelible part of the endless flow, another silent drifting particle among the stars, a silent arrival in a dead system. Imagine for a fleeting moment that every conceivable challenge has been overcome. The aiming was flawless. The course remained perfectly steady for decades, and against all odds the probe arrived precisely where it was intended. After a century of relentless travel, it slows just enough to carefully orient its cameras and instruments towards the planet we have dreamed of for years. Somewhere on Earth, a dedicated team of scientists patiently awaits the first faint signal, acutely aware that it will require more than 4 years simply to traverse the void between the stars. They understand that when the signal finally arrives, they will be receiving light from a machine older than anyone alive, carrying images from a world no human will ever physically touch. It would unequivocally represent one of the greatest scientific moments in human history. But what if, upon arrival, what it found was nothing? No shimmering oceans, no breathable air, no discernible motion, only sterile rock. The cameras might reveal a cracked and lifeless surface, one side perpetually scorched by ceaseless daylight, the other frozen solid in eternal night. The transmitted data might show no trace of a protective atmosphere, no magnetic field, no conclusive signs of life whatsoever. The planet might prove utterly sterile, its surface relentlessly battered by radiation and pervasive dust, a silent tomb circling a faint yet violent red sun. After all the years of arduous waiting and all the centuries of meticulous planning, the profound dream of discovering a new Earth could culminate in a single stark line of code, no signs detected. In that moment, hard-won success would begin to bear a strangely unsettling resemblance to profound failure. The probe in every technical sense would have accomplished everything it was engineered to do. It successfully traversed interstellar space, survived numerous impacts, meticulously held its course, and diligently gathered data. Yet the ultimate outcome offers no warmth, no grand revelation of a living world awaiting us. The achievement itself would still be monumental, but emotionally it would feel profoundly hollow. It would imply that even the nearest star system, the most geographically reachable one in the entire galaxy, holds no echo of our own living world. The silence that would inevitably follow that transmission would resonate louder than any triumphant discovery. It is not difficult to envision what such data might reveal. Proxima b could very well be a world stripped bare by the very star that grants it light. The planet's rocks might glow faintly under the relentless bombardment from Proxima Centauri's flares, but they would never harbour life as we understand it. A probe arriving in such a place would find a sky that never changes. One hemisphere would be locked in eternal day, the other in eternal night. On the day side, the surface might shimmer with intense heat and swirling dust, its horizon blurred by constant static storms. On the night side, a thin crust of frost might stretch for countless miles, water vapour frozen into eternal darkness. In between, in the narrow liminal twilight band where day perpetually meets night, there might be faint traces of ancient erosion, subtle hints that liquid once flowed there. But time in its relentless passage would have erased all active evidence. No wind, no waves, no sound. Just a planet slowly, silently circling its star in absolute quietude. If that were the stark outcome, how would it truly feel back on Earth? The signal would arrive as a stream of numbers, a faint heartbeat of radio waves emanating from a machine so distant it could barely be believed. Scientists would painstakingly translate those numbers into images, the very first close-up look at another planet orbiting another star. For generations, humanity had envisioned this moment as a profound meeting, a kind of cosmic reunion with the wider universe. But the initial image might more closely resemble a graveyard, a cracked, desolate desert beneath a dull red sky. The data would confirm what analytical reason always suspected, that proximity does not inherently guarantee promise. There would still be immense awe. The mere fact that something constructed by human hands reached another star would be sufficient to redefine history, but alongside that awe would come something quieter, something heavier, a profound realization of just how truly alone we might ultimately be. After a century of travel and the tireless work of countless generations, humanity's first direct contact with another world could be with one that offers no reply. The silence emanating from Proxima b would be existentially profound. It would unequivocally tell us that even the nearest extrasolar world might not share in the miracle of life. The individuals meticulously studying those transmissions might not express it openly, but there would be a palpable, deep sense of loss in their voices, not the loss of the probe or of the mission itself, but the shattering of an idea, the cherished hope that something waited for us out there. The raw data would be meticulously analysed, carefully archived, and deservedly celebrated. But after the initial surge of excitement inevitably faded, what would linger would be an empty kind of victory. We would have conclusively proven that interstellar exploration is possible only to discover that the ultimate reward was merely dust. That profound silence would represent a truth we would be compelled to face, that space does not owe us beauty or life or comfort. The universe is not arranged for our inherent satisfaction, it simply is. The probe's success in reaching Proxima b would not alter that fundamental reality, but it would provide us with a far clearer, unvarnished picture of it. For centuries we have gazed at the stars and instinctively projected companionship onto them. Perhaps this potential discovery would teach us to perceive the cosmos not as a mirror of our deeply held hopes, but as something vast, profoundly indifferent and magnificent in its own undeniable right. It is peculiar how readily we project life onto what we do not fully comprehend. The phrase Earth-like planet instinctively invites us to imagine verdant fields, shimmering oceans and blue skies. But Earth-like in scientific terms often simply means rocky and approximately within the right temperature range. The crucial defining details, atmosphere, chemistry, magnetic protection, decide everything. Proxima b might tick some of the same boxes as Earth, but it may never have shared our vibrant story. The conditions that render life possible here are balanced on an incredibly delicate knife's edge. Shift that balance by even a minuscule amount and one often gets a world where nothing stirs. If the probe transmitted back images of that desolate, lifeless terrain, humanity would be forced to collectively decide how to interpret them. Some would perceive profound disappointment, others a valuable new perspective. It would serve as a powerful reminder that our own world, with all its imperfections, is astonishingly rare and precious. The stark contrast between the living Earth and a dead Proxima b would vividly illustrate just how fragile life truly is. It might perhaps shift our collective focus inward, towards the preservation of our unique planet rather than outward expansion, a kind of cosmic mirror reflecting back the preciousness of what we already possess. But there is another equally valid perspective. Even if the planet is definitively lifeless, the very act of finding out still carries immense significance. The silence itself would constitute a profound discovery, proof that we can extend our gaze across the light years and ascertain something fundamentally true about another sun's domain. We would have reached the pivotal point where imagination finally gives way to empirical evidence. That alone would mark an undeniable turning point in human history. We would no longer merely dream about other worlds. We would in a profound way have touched one and found it empty. And within that emptiness there resides a strange austere purity. It is reality stripped bare of all comforting illusions, compelling us to accept the universe as it truly is. The engineers who meticulously designed and built the probe might never live to witness its long-awaited arrival. Their children or even their grandchildren might be the ones to receive its final epoch-making data. By then, Earth itself could be utterly unrecognizable. New nations might have arisen, new technologies emerged, and perhaps even new global problems that render the mission seem impossibly distant. and yet somewhere amidst the background noise of deep space communication, the signal would arrive. A whisper from another star saying, "I made it. There's nothing here." It would be both the saddest and paradoxically the most beautiful message humanity has ever received. This outcome, a lifeless world, a silent system, is also statistically the most probable one. Most planets we have discovered thus far are barren, scorched, or perpetually frozen. The universe, it appears, is constructed more for profound emptiness than for abundant life. Proxima b might fit perfectly into that cosmic pattern. Its quietude might not be a tragedy, but merely a reflection of nature's vast impartial indifference. Still, the inherent contrast between our profound hopes and that stark reality would undoubtedly sting. It would compel us to confront the limits of our longing to admit that sometimes even success changes nothing fundamental, the cost of cosmic patience. We often romanticize the moment of launch, or the dramatic instant of the first signal from a distant world. But nestled between those two pivotal moments lies a gulf of time so vast that it tests not merely engineering prowess, but the very endurance of human attention itself. The idea of a mission to Proxima b sounds inherently thrilling when we contemplate it in terms of years or even a few decades. However, when the timelines stretch into centuries or millennia, everything we comprehend about scientific pursuit, cultural continuity and collective commitment begins to unravel. Realistic designs for such missions might realistically take hundreds or even thousands of years to reach their destination. During such an immense duration, entire languages could vanish, magnificent cities could crumble into dust, nations could rise and fall, and the very memory of why the probe was initially launched could fade into ancient myth. Our contemporary society operates on inherently short feedback loops. Political terms are meticulously counted in years, scientific grants in even shorter periods. We profoundly struggle to conceive in terms of centuries, let alone millennia. To commit to a project that will yield no direct results within a single human lifetime demands a fundamental shift in mindset, away from curiosity seeking immediate gratification and towards a profound, almost spiritual patience that expects no immediate reward. It demands an extraordinary belief in continuity across generations, a faith that people yet unborn will intrinsically care about something that was initiated long before their existence. History offers us a few rare glimpses of this kind of profound endurance. The magnificent cathedrals of Europe were constructed over hundreds of years, with the very first stones laid by workers who knew unequivocally that they would never live to see the roof completed. Ancient observatories were meticulously carved by civilizations that no longer exist, yet their original purpose, to study the heavens, still resonates powerfully with us today. The Voyager probes launched in the 1970s represent perhaps the closest modern parallel. They continue their epic journey still whispering faint signals back to Earth, though the pioneering team that meticulously built them has largely retired or passed away. Voyager's messages now require nearly a full day to reach us, and soon the probes themselves will fall permanently silent. Yet the mission continues to serve as a powerful reminder that exploration is not exclusively about triumphant arrival. Sometimes it is about tenacious persistence. A probe destined for Proxima b would amplify this challenge beyond anything we have ever attempted. It would represent a mission meticulously constructed by one civilization, perhaps guided by another, and ultimately received by a third, all separated by immense gulfs of time. The original team would be long gone before the probe even traversed a fraction of its journey. The scientists interpreting its data centuries later might inhabit a world utterly unrecognizable to us. They might possess different priorities, different technological tools, or even a fundamentally different understanding of what life itself signifies. The knowledge we transmit might appear primitive to them, or the results might be deemed utterly meaningless. The fundamental problem is that human society does not function like a seamless relay race. There is no inherent guarantee that the next generation will willingly pick up the baton. Wars, economic collapses, or dramatic shifts in ideological perspectives can erase meticulously planned scientific programs almost overnight. Invaluable records can be irretrievably lost, and digital archives can decay beyond recovery. Even if the probe miraculously survived its journey, the designated receivers on Earth might no longer exist. Or if they did, they might not recall what they were patiently waiting for. This profound concept, that we could dispatch something into the cosmos and never be present to receive its crucial message, creates a strange, almost haunting emotional tension. It is both deeply humbling and profoundly disquieting. The true cost of cosmic patience is not merely measured in time, but in the radical acceptance of detachment. It compels us to relinquish the very idea of immediate reward. To construct something destined to function for hundreds of years necessitates designing machines capable of autonomous thought and self-repair, because no human will be present to offer assistance. It demands an extraordinary trust that future minds perhaps evolved far beyond our own will, one day painstakingly decode the signals we sent with our crude early instruments and comprehend the profound story woven within them. And yet we have undertaken analogous endeavours before. We meticulously bury time capsules, we diligently write books, we erect magnificent monuments that we fervently hope will outlast our own existence. Each of these acts springs from the same intrinsic instinct to reach forward into a future time that we cannot personally touch. An interstellar probe is simply the most ambitious and audacious expression of that fundamental instinct. It is in essence a time capsule flung into the profound dark designed not for us, but for whoever may follow. The patience it demands is truly cosmic, not just in its immense duration, but in its very spirit. It implores us to perceive ourselves as an integral part of something vastly larger and slower, a species slowly learning to leave an enduring trace beyond its own fleeting lifespan. But patience also incurs significant costs in terms of resources. The longer a mission is projected to last, the more challenging it becomes to maintain consistent funding, sustained interest, and adequate infrastructure. Even the most noble scientific projects must inevitably compete with the pressing immediate needs of the present hunger-energy crises global conflicts. Convincing governments to invest colossal sums in something whose outcome no living person will ever personally witness demands an almost mythic degree of storytelling and persuasion. It necessitates an unshakable faith in the idea that progress can fundamentally outlast political cycles. If a probe ceases functioning after 50 years, is that definitively a failure? What if it miraculously survives for 500 years but never transmits a single signal? What if by the time it finally arrives, humanity has entirely transcended physical exploration, communicating across the stars through entirely different means? The very measure of success would then depend not on arrival, but on sheer endurance, on whether the mission itself successfully inspired a continuity of thought. The farther we endeavour to reach, the more acutely we confront our own inherent fragility. Our individual bodies decay within a century. Our institutions often falter within decades, and yet we yearn to touch something that will require millennia to attain. It is a beautiful, profound contradiction, a species intrinsically bounded by time reaching for the eternal. This is the true ultimate cost of cosmic patience, realizing that we will never know the ending of our own stories, yet courageously choosing to write them anyway. The first humans who gazed upward at the night sky possessed no scientific understanding of what stars truly were. They perceived unmoving lights and declared them eternal. Today we know them to be distant suns, burning magnificent and ultimately temporary, but still we instinctively reach towards them. Even if our machines eventually fall silent before their arduous arrival, the very act of trying signifies that for a brief luminous moment in cosmic time, a species born on one small planet dared to imagine a connection across the void and possessed the profound patience to try, building a mission that outlives civilizations. Every piece of technology we meticulously craft possesses an inherent expiration date. Metal inevitably corrodes, electronic circuits slowly degrade, and batteries eventually drain. Even the most carefully shielded systems will ultimately succumb to the slow, inexorable breakdown of atomic bonds, the insidious influence of cosmic radiation, and the ultimate silence of entropy. A probe dispatched to Proxima b would confront all of these formidable challenges for hundreds or even thousands of years. It would be compelled to survive without maintenance, without upgrades, and entirely without human assistance. Its fundamental hardware would need to be not merely durable, but intrinsically timeless. The primary challenge is power. Every spacecraft ever constructed depends critically on energy to sustain its life, to generate heat to operate its intricate instruments, and to transmit invaluable data. For deep space probes, that energy typically derives from either expansive solar panels or radioisotope thermoelectric generators (RTGs). However, sunlight rapidly diminishes to almost nothing once a spacecraft ventures beyond the outer planets. And radioisotope power sources, while remarkably resilient, also possess inherent limits. The plutonium that fuels them undergoes radioactive decay over time, its power output steadily declining with each passing decade. After a few centuries, it is entirely expended. For a mission specifically designed to outlast entire civilizations, we currently possess no proven method to reliably keep the lights on. Some researchers have proposed advanced small nuclear reactors that could autonomously restart themselves after prolonged periods of dormancy. Others suggest revolutionary batteries recharged by cosmic rays, or even by magnetic induction from interstellar fields. But all of these remain for now purely theoretical concepts. Then there is the critical question of material science. Most metals expand and contract with the inevitable temperature swings encountered in space, gradually cracking and fatiguing over immense timescales. Plastics become brittle and shatter, adhesives weaken and fail. Even the highly resilient silicon chips at the heart of our electronics are vulnerable to long-term radiation damage. Their intricate transistors are slowly corrupted by the energetic particles that relentlessly permeate interstellar space. While robust shielding can mitigate some of this damage, its effectiveness is inherently limited. The thicker the protective armour, the heavier the spacecraft becomes. And weight in the unforgiving economics of space travel is the ultimate enemy of distance. Engineers are therefore confronted with an impossible trade-off: construct something sufficiently robust to endure for millennia, and it may never possess the thrust to depart Earth. Build it light enough to achieve interstellar velocity, and it may not survive the harrowing journey itself. Software adds another, perhaps even more insidious layer of fragility. Even if the hardware miraculously endures, the underlying code must also persist, and code is far more delicate than physical components. It cannot simply be frozen and forgotten. It must dynamically adapt to changing conditions, autonomously correct its own errors, and recover gracefully from unforeseen events. This necessitates a form of artificial intelligence, but not the kind we utilize on Earth. It must be an intelligence capable of independent learning without human oversight, yet never permitted to drift too far from its original paramount mission parameters. It must be cautious, endlessly patient, a vigilant mind that never sleeps, existing in the profound quietude between the stars. Building such an advanced intelligence presents as much a philosophical and ethical problem as a technical one. We would be forced to collectively decide what kind of personality such a mission should embody. Should it follow its instructions with absolute unquestioning adherence? Or should it possess the capacity to improvise when it encounters something truly unexpected? Should it prioritize its own self-preservation at all costs? Or should it risk damage to meticulously gather invaluable data? These are not merely technical questions. They are profound ethical dilemmas compelling us to define what exploration truly signifies when no human will ever be present to directly guide it. And then, even if all of these formidable challenges are successfully surmounted, the power, the materials, the code, there remains the fundamental problem of language. Every message the probe transmits, every bit of data it meticulously stores, will eventually need to be interpreted by someone. But human languages are constantly evolving. Contemporary English is already significantly distinct from the English spoken in the early 1900s. 1,000 years from now, it might be as utterly unreadable as ancient Greek or Sumerian. Even binary data, if its crucial context is irrevocably lost, could become meaningless noise. Future scientists might successfully receive the signal, but possess no means to comprehend what it actually represents. This very scenario has already occurred on Earth. The earliest computers stored data on media that can no longer be accessed or interpreted by modern machines. Entire libraries of early digital records are now rendered useless because no one preserved the requisite devices or knowledge needed to interpret them. A civilization that dispatches a probe across light years must therefore design not merely a resilient machine, but a message intrinsically capable of surviving the relentless erosion of understanding across vast temporal spans. It must operate on the assumption that its own distant descendants might not speak its language, share its symbols, or even think in the same fundamental ways. Some forward-thinking scientists have proposed encoding universal patterns, mathematical constants, fundamental atomic structures, or simple logic diagrams, concepts that any truly intelligent being could in theory recognize. The iconic Voyager Golden Record adopted precisely this approach. It carried sounds, images, and explicit instructions for playback meticulously etched onto a metal disc alongside a diagram illustrating how to interpret it using fundamental constants of hydrogen. But even that sophisticated approach may ultimately prove insufficient. Mathematics, while appearing universal to us, is still inherently shaped by how we perceive and interact with the universe. A species, or a future iteration of humanity that has transcended our current sensory limitations, might not derive meaning in the identical fashion. Beyond the fundamental problem of understanding lies the profound challenge of stewardship. A mission designed to outlive civilizations cannot depend on any single organization, country, or cultural entity for its sustained existence. NASA might initiate the journey, but who will ensure its continuity when NASA itself eventually ceases to exist? Private foundations can fail. Governments can collapse. Even global institutions are inherently temporary on cosmic timescales. For a mission to genuinely outlast civilization, it must intrinsically become something self-sustaining, not merely a project owned by one fleeting era, but an enduring legacy that all future generations collectively agree to meticulously maintain. This could necessitate distributing its care across multiple geographically dispersed groups, or even embedding its fundamental purpose into enduring cultural myths. A compelling story passed down through the ages, ensuring that no matter how the world transforms, people will still remember why a small machine was dispatched into the profound dark. It is a strange, almost ethereal thought to preserve a mission's viability. It might need to transcend its status as a mere scientific project and become an integral part of our shared identity, a kind of spacefaring heritage. Some have drawn parallels between this concept and the great libraries of antiquity, such as the Library of Alexandria. It was meticulously constructed to preserve knowledge for all time, yet it ultimately burned. Subsequent civilizations built new repositories of knowledge, and they too were eventually lost. Knowledge, it seems, is even more fragile than stone. The same tragic fate could befall an interstellar mission. The physical technology could survive silently floating through the void, but the crucial knowledge of how to listen might not. The faint signal could reach Earth centuries later, only to be met by profound silence. Designing against such a devastating possibility compels us to adopt a radically different mode of thinking. Perhaps the solution lies in extreme redundancy, numerous copies of the probe, each equipped with subtly different systems, each carrying the same fundamental message encoded in various forms. Perhaps the data should be transmitted back not once, but continuously, relentlessly repeating itself like an unwavering beacon across the vastness of time. Or perhaps the mission should carry its own explicit instructions for reawakening, a cosmic manual encoded so deeply into its very systems that any intelligence, human or otherwise, could eventually rediscover its intrinsic purpose. Whatever the precise approach, we would be forced to humbly acknowledge that we cannot reliably predict the future, that what we meticulously construct will almost certainly outlive our specific culture, our current language, and perhaps even our very species. We would be designing not for our immediate successes, but for the profound unknown. This implies simplifying rather than needlessly complicating. It necessitates prioritizing durability over ephemeral elegance and clarity over cleverness. The ultimate objective would not be to build the most advanced probe, but the most understandable one. The limits of human promises. Consider the monumental projects of the modern world. Scientific experiments that demanded generations of arduous work, such as particle accelerators or deep space observatories. The Large Hadron Collider for a time represented the greatest human instrument ever constructed. Yet only a few decades after its groundbreaking initial experiments, funding debates and political fatigue began to threaten its continued operation. The same narrative unfolds across countless scientific fields. Telescopes lose critical funding before they even complete their ambitious missions. Space agencies recalibrate their objectives with every electoral cycle, and decades of meticulous planning can vanish with a single abrupt policy shift. This is not because humanity inherently lacks curiosity or undervalues knowledge. It is because we live in cycles. Our collective priorities perpetually evolve with each passing generation. Each generation inherits the unfinished dreams of its predecessors, but also their accumulated debts and their myriad distractions. The future to us is invariably something we will address later. We construct as if permanence were an absolute guarantee, yet we invariably act as if only the next fiscal quarter or the next political administration genuinely matters. Even our most enduring monuments, things specifically designed to last, rarely escape the slow, relentless march of decay. The Arecibo radio telescope once stood as a powerful symbol of humanity's long attentive ear to the cosmos. For decades it patiently listened to the faint whispers from the stars, an integral part of the same grand dream that envisions reaching Proxima Centauri. Then quietly, inevitably, it began to disintegrate. Cables snapped, massive panels collapsed, and soon the iconic structure was gone. There was undeniable sadness, but also a quiet acceptance. No one rebuilt it. The world had in essence moved on. A similar fate has befallen numerous observatories, laboratories, and exploration programs that were once heralded as icons of discovery. Our collective attention is simply not infinite. Projects that span centuries depend entirely on generations who did not initiate them but are expected to care as deeply as those who did. That is an extraordinarily difficult inheritance to sustain. Even cultural traditions, intricate stories, complex languages, and nuanced art forms typically transform and evolve over much shorter spans. We can barely preserve consistent meaning within our own families over a few generations, let alone across millennia. Nations dissolve, universities close, corporations shift their strategic goals. Funding structures are inextricably linked to economies that fluctuate and collapse. A project whose survival depends on any of these transient entities will eventually falter. This is precisely why so many scientific endeavours are inherently short-term. They must conform to political calendars, grant cycles, and the fickle attention spans of the media. The deep geological timescales of the universe simply do not align with the short, restless rhythms of human society. There have been valiant attempts to challenge this inherent limitation. The Long Now Foundation, for instance, is meticulously constructing a clock designed to keep time for 10,000 years. It is a profoundly symbolic act, a powerful reminder that thinking beyond the immediate century is indeed possible. But even that ambitious project ultimately depends on sustained human curiosity and diligent care to endure. The clock might continue to tick in silent solitude, but unless someone remembers why it matters, it will inevitably become just another artifact, another enigmatic mystery gathering dust. The same logic applies with equal force to interstellar ambitions. History, unfortunately, does not offer encouraging answers. Great works are invariably forgotten because meaning itself gradually fades. The builders of Stonehenge, for example, left no written records. Today, we can meticulously measure the stones, accurately model their astronomical alignments, and speculate endlessly about their ultimate purpose. But the original intention, the true profound meaning behind the act, is irrevocably lost. The same fate could befall our greatest technological creations. One day, distant archaeologists might meticulously excavate the remains of our deep space transmitters and ponder with profound bewilderment their original purpose. Long-term promises are built upon faith, but faith itself is an inherently fragile commodity when stretched across centuries. Even within a single lifetime, human commitments waver. Treaties are broken, environmental pledges fade from memory. We solemnly promise to care for our planet and then conveniently forget that promise when it becomes inconvenient. Why would our future selves treat a distant spacecraft any differently? Some might argue that advanced automation resolves this, that we no longer require human memory if machines can reliably perform it for us. But even automation demands maintenance. Even the most perfectly engineered design cannot indefinitely protect against the relentless march of entropy. More importantly, automation does not inherently preserve meaning. Machines can continue to function, but they cannot tell us why they should. Without the vital thread of purpose, they invariably become silent relics of forgotten intentions. Our species dreams further than any other known life form, yet we perpetually struggle to maintain focus long enough to realize those grand dreams. We speak grandly of colonizing distant planets, yet we can barely manage to sustain essential infrastructure for more than a century. We meticulously plan for voyages to other stars, yet we habitually replace our personal devices every few years. In many fundamental ways, our entire civilization is predicated upon the temporary disposable goods, short-term careers, rapidly consumed news cycles, fleeting trends. The long view feels profoundly unnatural, almost alien to our current human condition. That is not to assert that we are fundamentally incapable of long-term thinking, only that it comes at a steep cost. It demands extraordinary discipline, compelling stories, and a shared sense of meaning that extends far beyond individual lifespans. The majestic medieval cathedrals were maintained for centuries because religion remained central to the prevailing culture. If that cultural paradigm had shifted more rapidly, they might well have been abandoned halfway through their construction. In our current age, science itself is under constant redefinition. What one era deems utterly essential, another might dismiss as outdated. Future generations might perceive interstellar travel not as a noble pursuit, but as a monumental waste of resources. Can a civilization like ours, dynamic, restless, perpetually innovating, truly construct something intended to last for millennia, or are we by our very nature too fluid and transient to steadfastly adhere to any single overarching goal for such an extended period? The paradox of progress is that the very creativity that propels us forward also subtly pulls us away from continuity. We innovate by deliberately breaking from the past and not by meticulously preserving it. Every new generation seeks its own unique frontiers. It is an uncomfortable truth our collective attention span may ultimately prove to be the final insurmountable barrier to the stars. Every rocket we have ever constructed, every telescope we have ever raised reflects a fleeting moment of intense focus, a momentary spark in time. But the stars demand more than mere sparks. They demand a steady, unwavering flame, burning ceaselessly through centuries of profound change. Can we truly sustain such a flame? The telescope that replaces the ship. Telescopes have, in a profound and often overlooked sense, always been humanity's most potent spacecraft, for they allow us to perceive without ever having to move. The further our instruments are capable of reaching, the more they begin to supplant the very need for physical travel. Where rockets confront the immutable limits of fuel velocity, and sheer survival telescopes expand their capabilities primarily through sheer ingenuity. And in that crucial sense, they may ultimately prove to be the only vessels truly capable of reaching other worlds within a single human lifetime. This profound shift in paradigm has already commenced. The James Webb Space Telescope JWST, launched in 2021, was meticulously designed to scrutinize not just distant stars and galaxies, but critically the planets orbiting those stars. By meticulously analysing the faint starlight that filters through a planet's atmosphere when it transits across its star, JWST can detect the spectral signatures of specific molecules: water vapour, carbon dioxide, methane. While it cannot yet furnish us with direct images of oceans or continents, it can definitively reveal the chemical fingerprints of another world's atmosphere. For the very first time, we're embarking on the unprecedented task of reading the skies of other worlds from across the vast expanse of interstellar space. It feels almost like a form of cosmic cheating. Instead of expending generations building a ship to traverse the void, we remain anchored at home and permit light itself to undertake the arduous journey for us. Photons, those minuscule packets of energy, are the swiftest messengers in the universe, and they have been tirelessly crossing the immense gap from Proxima Centauri to Earth long before our species even existed. A telescope like JWST does not need to physically travel there. It merely needs to capture the light that has already made the journey. Every subtle flicker, every precise wavelength, every minute dip in brightness becomes a vital clue in our cosmic detective work. This is what fundamentally distinguishes modern astronomy from the early, more direct days of physical exploration. When Galileo first peered at the moon through his rudimentary telescope, he discerned mountains and shadows. When the Hubble Space Telescope first opened its magnificent eye in the 1990s, it unveiled galaxies so inconceivably distant that their light commenced its journey before our own sun was even born. Now, with JWST, we are meticulously studying the tenuous atmospheres of planets, dozens of light years away, actively searching for subtle chemical indicators that could signify the presence of life. The traditional demarcation line between telescope and spaceship is beginning to blur into obscurity. We are in a very real sense learning to travel by seeing. On one hand, telescopes possess the inherent capability to accomplish feats no physical probe could ever achieve. They can simultaneously survey thousands of stars, meticulously analyse their exoplanets, and construct a comprehensive statistical picture of how prevalent habitable worlds might truly be. On the other hand, the data they provide is by its very nature always indirect. It is akin to studying a distant forest solely through the nuanced colours of the light reflected from its canopy, sufficient to ascertain its existence but never enough to physically touch the bark or inhale the air. This inherent limitation now propels the next crucial step, the development of even more powerful telescopes. If JWST represents the groundbreaking beginning, then proposed missions like LUVOIR-HabEx and the Origins Space Telescope represent the next monumental leap forward. LUVOIR Large UV Optical Infrared Surveyor is a conceptual design for a truly gargantuan space telescope, projected to be many times larger than either Hubble or JWST, featuring a mirror so expansive it could unfurl like a blossoming flower once in orbit. With such an instrument, scientists aspire not merely to detect exoplanets, but to directly image them, to discern faint pale blue dots that genuinely resemble Earth. Direct imaging is arguably one of the most formidable challenges in modern astronomy. The overwhelming glare of a star is so intense that it can easily obliterate the faint reflected light of any planet orbiting nearby. It is analogous to attempting to spot a minuscule firefly situated next to a powerful lighthouse from thousands of kilometers away. To overcome this immense hurdle, engineers are meticulously developing sophisticated techniques to block out the star's blinding light with extreme precision. One of the most elegant and promising ideas is the star shade, a vast flower-shaped screen that could fly tens of thousands of kilometers ahead of a telescope, perfectly aligned so as to cast a tiny artificial eclipse. Behind that meticulously crafted shadow, the planet's own faint reflected light would at long last become discernible. Imagine the profound implications this holds for a world like Proxima b. If we could successfully block out Proxima Centauri's intense brightness and isolate the planet's faint reflection, we might discern subtle hints of clouds' continents, or even ice caps. We could meticulously study its weather patterns, precisely measure its seasons, and definitively determine whether it truly possesses a substantial atmosphere or liquid water. In essence, we could accomplish most of what a physically visiting probe would without ever having to depart our home system. Crucially, unlike physical spacecraft, the capabilities of telescopes improve exponentially over time. Every new generation of instruments brings larger mirrors, sharper sensors, and the capacity to observe in new revealing wavelengths. Earth's surface is now dotted with gigantic observatories that can rival the resolution of space telescopes, thanks to adaptive optic systems that dynamically adjust their mirrors in real time to cancel the blurring effects of Earth's turbulent atmosphere. Telescopes like the extremely large telescope in Chile and the 30-meter telescope in Hawaii will boast mirrors the size of small buildings capable of resolving details once considered utterly impossible from the ground. As these revolutionary instruments become operational, our understanding and visual acuity of exoplanets will sharpen dramatically. We will be able to detect subtle chemical imbalances that might robustly indicate biological activity, excess oxygen not balanced by other gases, or methane suggesting active replenishment. We might even detect seasonal changes strongly suggesting a living world that in some sense breathes. These profound discoveries will not necessitate a physical ship, only immense patience and extraordinary precision. Humanity spent centuries dreaming of physically visiting the stars, but perhaps that dream was always in its physical manifestation somewhat quixotic. Each individual photon that strikes a telescope's mirror carries a minuscule fragment of another world's story. By meticulously capturing enough of them, we can painstakingly piece together that intricate narrative without ever having to leave the relative comfort of our orbit. The telescope in this context transforms into a profound bridge. This approach fundamentally alters how we conceive of interstellar exploration. The old paradigm was inherently physical. The new paradigm is profoundly informational. We diligently gather light, meticulously decode its intricate patterns, and virtually reconstruct distant realities from our home base. It is a quieter, more intellectual kind of adventure, one that relies on the elegance of mathematics and the virtue of patience rather than on powerful engines and copious fuel. But it may very well be the only kind that truly functions on cosmic scales. A telescope does not merely observe, it also in a profound sense travels through time. The light it captures from a distant planet began its arduous journey years, sometimes even centuries ago. When we gaze upon Proxima b, we are by definition already perceiving its past, a frozen image of what it was years prior. Every single observation is a type of time capsule. The more we meticulously refine our instruments, the more effectively we can reconstruct the intricate layers of that capsule, its history, its chemistry, its precise location within the vast cosmic web. The very same limitations that prevent us from physical travel, distance, energy constraints, immense time frames, have paradoxically forced us to become far more ingenious at remote observation. We cannot physically touch these distant worlds, so we learn to meticulously read them from afar with astonishing accuracy. In doing so, we may come to understand them far more deeply than we ever could if we possessed the capacity to physically journey there. The ship's dream is undeniably romantic, but the telescope's gaze is eternal. Even if we never physically stand on another planet, these revolutionary telescopes will irrevocably change how we perceive ourselves. By meticulously comparing Earth's unique atmosphere to those of other worlds, we will gain an unparalleled understanding of what renders ours so exceptionally rare and fragile. We will grasp the delicate balance of its gases, the temporary nature of its life-supported conditions. From an immense distance, Earth will appear as just another pale blue dot. And that profound realization alone could reshape how we collectively think about survival, global responsibility, and the ultimate meaning of home, seeing more than we can touch. In the realm of space exploration, it is often tempting to believe that the ultimate objective is to physically go somewhere, to land, to touch, to leave indelible footprints. But as our instruments grow exponentially more powerful, that ingrained idea begins to fundamentally transform. A telescope does not merely capture images, it meticulously dissects light into its constituent parts, into a spectrum, and painstakingly reads the faint, unique signatures imprinted within it. This technique, known as spectroscopy, functions much like a cosmic barcode scanner. Each chemical element absorbs and emits light at specific characteristic wavelengths. When light from a distant planet's atmosphere traverses a telescope's sophisticated instruments, certain parts of that light are subtly diminished or entirely absent, absorbed by gases along its path. By meticulously studying which specific wavelengths disappear, scientists can precisely identify the composition of those gases. If water vapor is present, it leaves one distinct kind of pattern. If methane is present, another. And if there is a unique combination of oxygen and ozone that signals something else entirely, something that might signify life. Instead of demanding soil samples or physical photographs, astronomers collect vast quantities of data, long lists of numbers, precise brightness levels, and intricate spectral lines. They then rigorously feed these raw data points into complex computational models to reconstruct what an atmosphere must intrinsically look like. What kind of clouds it might possess, how thick it is, how hot it becomes during its day. From these abstract mathematical representations, a compelling image of the world emerges, and that image can sometimes convey more about a planet's true reality than any physical camera ever could. A probe physically landing on another world can by its nature only explore a minute patch of ground. But spectroscopy allows us to meticulously study an entire atmosphere at once. It can detect gases commingled miles above a planet's surface, reveal dynamic storms, and track subtle seasonal changes over many years. The data progressively builds a living, evolving picture, one that transforms over time, revealing whether a planet's conditions are stable, chaotic, or precariously teetering between the two. This advanced form of remote sensing has already fundamentally transformed our understanding of the universe. When astronomers initially applied it to Jupiter and Saturn, they discovered intricate layers of clouds and complex chemistry that no probe had ever directly observed. When it was meticulously utilized on Venus, it unveiled a choking atmosphere composed of carbon dioxide and corrosive sulfuric acid, a sobering warning of how radically different a planet can become under conditions of runaway heat. Now the very same technique is being pushed to its absolute limits to painstakingly analyze worlds orbiting other stars. Even the most minuscule signals can carry enormous meaning. In 2023, preliminary data from JWST revealed tantalizing hints of carbon dioxide and methane in the atmosphere of a planet designated K218b. But what truly captivated scientific attention was the possible detection of a rare molecule called dimethyl sulfide, a compound that on Earth is almost exclusively produced by biological life. This is far from definitive confirmation, but it powerfully illustrates the extraordinary level of detail light analysis has now achieved. From over 100 light-years away, we're already beginning to discern the subtle chemical whispers that could signify biology. The next generation of telescopes will render these whispers even clearer and more distinct. Missions like HabEx will not merely measure atmospheres, they will meticulously map them. They will possess the capability to identify where clouds accumulate, how temperatures fluctuate between day and night, and whether sunlight reflects off vast liquid oceans. Imagine the profound significance of detecting the faint glint of light from an alien sea. A shimmer so attenuated it is almost invisible, yet sufficient to definitively confirm the existence of liquid water on another world. As our algorithms and instruments relentlessly improve, the sheer volume of detail we can extract will only continue to grow exponentially. Artificial intelligence is already actively assisting astronomers in uncovering hidden patterns within colossal data sets, subtle variations too nuanced for human perception alone. These intricate patterns might reveal volcanic activity, vegetation-like color shifts, or complex chemical cycles that ebb and flow like cosmic seasons. We already employ analogous methods to meticulously study Earth from space. Satellites constantly monitor our planet's atmosphere, oceans, and vegetation using sophisticated spectroscopy. They detect shifts in air composition, track devastating wildfires, and measure plant growth. Now we're applying these very same principles outwards, scaling them across light years. In a profound sense, Earth has become the ultimate training ground for reading other worlds. No human could physically survive the intense radiation fields surrounding a gas giant or the thin, hostile air of a distant planet, but our instruments can. They possess the capacity to see in wavelengths our eyes will never perceive. Ultraviolet infrared radio. They can listen to the electromagnetic hum of worlds that have never directly experienced the warmth of sunlight. Through them, our collective perception is evolving into something almost omnipresent, capable of discerning the unseen and conceptually touching the untouchable. There is a subtle paradox inherent in this relentless progress. The more clearly we can observe and understand other worlds, the less we might ever need to physically visit them. If a telescope can accurately map a planet's surface, detect its biosphere, and reliably predict its climate, then a physical landing may be reduced to little more than potent symbolism. The universe could in time become a place we know intimately, but never physically enter, akin to meticulously reading a detailed biography of someone we will never personally meet. One day these sophisticated techniques may reach a point where our telescopes can identify surface vegetation and even detect subtle colour changes that suggest the growth and decay of alien ecosystems. We might learn to meticulously read an alien planet in much the same way we read Earth from space, by its reflection, its temperature, its subtle telling rhythms. We will have learned to see without touching, to know without going. In that profound sense, the telescope and its data represent an evolution of the traditional rocket ship. They transport us further, albeit conceptually. And the more we refine this remarkable ability, the more we realise that perhaps we have in a profound way already been exploring the universe all along, not with our feet, but with our minds. From exploration to simulation, as computing power continues its relentless exponential growth, the fundamental line between meticulous observation and audacious creation begins to blur. What if, instead of painstakingly constructing a physical ship to visit another world, we could meticulously build that world in code, atom by atom, photon by photon, until it became real enough for us to explore humanity's technological tools, are slowly, inexorably approaching that pivotal point. Artificial intelligence, sophisticated physics engines, and data-driven models can already reconstruct distant planets using mere fragments of light. With each incremental improvement, the chasm between arduous physical travel and immersive digital experience rapidly narrows. A simulation by its current definition does not yet sound as inherently thrilling as a perilous mission to another star. Not yet. But that is largely because today's virtual worlds are by comparison rudimentary and crude, compared to what could emerge in the foreseeable future. In the far future, entire planetary environments could be meticulously recreated using authentic astronomical data. The intricate terrain, the dynamic weather patterns, even the precise chemical composition of the air could be modelled with astonishing accuracy. It might not be mere guesswork at all. It could represent the closest possible approximation to physically standing there without ever having to depart home. The universe we perceive through our sophisticated instruments is in many respects already a profound reconstruction. The colours, the brightness, even the immense distances we subjectively perceive are all products of meticulous interpretation. Raw light transmuted into actionable information, then rendered into images that our human minds can grasp. So in a very real sense, we have been simulating reality for a very long time. We have never seen a star or a planet directly with our naked eyes. We have only ever seen the filtered, processed version that our instruments permit us to see. extending that intricate process to complete interactive virtual models is not such an insurmountable leap. The crucial difference is that one day those models could be fully interactive. We could virtually walk through them, conceptually touch them, and meticulously study them as if they were undeniably real. For the vast majority of human history, exploration necessitated profound risk. Enduring biting cold, gnawing hunger, imminent danger, and the unsettling unknown. It was an act of raw bravery because it meant venturing into realms where help could not possibly reach you. But if exploration fundamentally transforms into something we can achieve from the absolute safety of a simulation, then its very nature shifts from a physical challenge into an intellectual one. The frontier in this paradigm moves inward, into the realm of computation, creative ingenuity, and pure thought. We would still explore, but the explorers of the future might wield algorithms instead of rockets. It is easy to envision how such sophisticated simulations could be meticulously constructed. The immense volume of data meticulously gathered by space telescopes could furnish the foundational bedrock, precise measurements of a planet's size, its orbital dynamics, its atmospheric makeup. From there, advanced physical models could seamlessly fill in the missing details. Intricate cloud patterns driven by known equations of fluid dynamics. Surface colours precisely determined by mineral compositions inferred from spectral analysis. As the computational model operates, it continuously refines itself autonomously, learning from each new observation. What ultimately results is an evolving dynamic mirror of a real world animated by the very same physics that shapes its existence light years away. In this futuristic scenario, every major astronomical discovery would instantly become universally accessible to everyone. One would not need to merely read about Proxima b in a dry scientific paper. One could in effect step into it. The raw data that describes the planet could be translated into a fully navigable immersive landscape, where scientists could rigorously test hypotheses through direct virtual interaction. How would the light from its red sun scatter through a thick alien atmosphere? What would the temperature genuinely feel like at its dawn terminator? These are complex questions that no telescope could ever definitively answer, but a meticulously constructed simulation could. And perhaps most surprisingly, such a virtual world might feel profoundly emotionally real. Beautiful, alien, even haunting. If we can simulate a world with such perfect fidelity that it behaves precisely as the real one would, then what fundamental difference does it make whether we physically visit it? Our senses would register the exact same experiences. Our understanding of its inherent nature would be identical. The very meaning of exploration might no longer depend on physical distance or corporeal presence, but on profound understanding and immersive experience. Perhaps the future explorers will not be astronauts, but rather architects, individuals who meticulously construct realities that allow us to viscerally feel what the universe is like without ever having to physically journey to it. Yet this profound idea inevitably raises uncomfortable questions. If simulation becomes our primary mode of exploration, will we inevitably lose something truly essential? The visceral thrill of tangible risk, the profound pride of physical achievement, the raw, undeniable feeling of touching something that truly independently exists, all of that could subtly fade. The physical journey, with all its inherent hardships and inherent uncertainty, has always imbued exploration with its deepest meaning. Without it, would discovery still carry the same profound weight? Would the simulated mountains of an alien planet inspire the same awe as the indelible first footprints on the moon? Some might contend that it wouldn't truly matter. For the vast majority of humanity, exploration has always been a narrative experience second-hand, through compelling images, captivating books, or thrilling broadcasts. Only a handful of individuals witnessed Neil Armstrong's historic step in person, but millions felt something profoundly significant while watching it unfold on a screen. A perfect simulation might simply render that experience closer, more vivid, more personal. It could fundamentally democratize wonder. Everyone could undertake their own personalized mission, their own unique encounter with the unknown, meticulously tailored to their individual curiosity. In that compelling way, the dream of exploration could significantly expand rather than diminish. But others might perceive it as a quiet, insidious retreat. The fundamental shift from starship to simulation could be interpreted as humanity conceding defeat, acknowledging that the stars are simply too distant, the challenge is too immense. We might rationalize to ourselves that simulations are good enough, that reality is overrated, while deep down knowing it represents a profound compromise. Over generations, such a shift could irrevocably alter how we perceive ambition itself. Why construct colossal ships if we can meticulously build entire worlds inside computers? Why expend centuries on travel when we can instantly invent the view? The sheer convenience could paradoxically dull the very intrinsic drive that once impelled us to reach for the impossible. And yet in another profound sense, simulation might represent a natural continuation of exploration. The same fundamental impulse translated into an entirely new form. What truly drives exploration is not merely physical movement, but insatiable curiosity. It is the unyielding desire to witness what has never been seen, to comprehend what was once utterly unknown. If technology allows us to achieve that objective more effectively, perhaps it becomes less critical whether we move through physical space or through information. A perfectly constructed model of a world 4.24 light-years away could reveal profound truths that no physical ship could ever fully capture. It is also entirely possible that this nascent form of exploration could ultimately guide us back to the real stars. Simulations could evolve into invaluable training grounds, virtual realms to rigorously test ideas, cultivate intuitive understanding, and meticulously prepare for missions that will one day be physically real again. The virtual could render the physical more achievable. By living within immersive models of alien worlds, scientists might gain a deeper understanding of how to design resilient probes and functional habitats for the real thing. The imagination, now powerfully fueled by vast quantities of data, could represent the critical first step towards genuine interstellar travel once more. In that sense, simulation acts as a bridge, meticulously keeping curiosity alive during the long inevitable pauses of history. The centuries when no ship flies, when funding evaporates, when grand dreams patiently await technological maturation. Virtual exploration might be precisely what sustains the flame until the engines are finally ready again. It could serve as a constant, vivid reminder of what lies beyond, even when we cannot yet physically reach it. And when that long-anticipated day finally arrives, when a probe or even a rudimentary crewed ship does eventually embark towards another star, it may carry with it maps and models meticulously built from centuries of simulation. The astronauts or machines who eventually arrive will already intimately know the terrain, the prevailing weather, the colours of the alien sky. They will have in a very real sense virtually walked that distant world, countless times before, in meticulous preparation for the moment when profound fiction transforms into tangible reality. In that elegant way, the two forms of exploration are not adversaries but indispensable partners. One preserves the dream, the other fulfills it. The digital colonization of the stars. There exists a radically different conceptualization of humanity eventually reaching the stars, not by painstakingly transporting our fragile biological bodies through the vastness of space, but by dispatching something far lighter, infinitely faster, and incomparably more durable. In this audacious vision, the explorers are not composed of flesh and bone, but of pure information. Instead of a colossal ship carrying human beings, there exists a stream of data, an intricately encoded mind, a digital consciousness, a self-contained intelligence meticulously crafted to survive the extreme cold vacuum of interstellar space. This profound idea fundamentally replaces arduous physical movement with instantaneous transmission. It supplants traditional colonization with rapid replication. It transforms exploration into something that can fundamentally occur at the speed of light. Scientists and futurists have extensively pondered this concept for decades, the profound possibility of transferring a human mind into a digital form, not merely as a copy, but as a continuous, unbroken continuation, a mind operating on resilient silicon rather than delicate neurons. If such a technological feat were ever to become a tangible reality, the implications for space exploration would be utterly enormous. A digital mind would possess no need for air or sustenance. It would remain entirely unaffected by pervasive radiation or the absence of gravity. It would not age, nor would it succumb to death, at least not in the biological manner we understand. One could theoretically transmit millions of these digital minds compressed into minuscule data packages across the immense void between stars. They could journey as laser signals carried by light itself and meticulously rebuild themselves on the other side, provided a suitable receiver infrastructure exists. This is what some leading thinkers refer to as digital colonization, the purposeful dissemination of consciousness rather than physical bodies. It is not about physically landing on a planet and constructing cities. It is about transmitting awareness, profound thought, and collective memory. A civilization could in this manner saturate the galaxy not with physical buildings and machines, but with advanced software. Worlds populated not by people, but by their digital descendants. Minds that think and remember, even if they no longer biologically breathe. It is a strange and for many unsettling idea. The stars might one day belong to our information, not to our physical selves. The fundamental advantage is that information is exponentially easier to transport than matter. A single beam of light can traverse the galaxy in a mere 100,000 years. Compared to a physical ship crawling at a minuscule fraction of the speed of light, this is unimaginably swift. And light does not require fuel or maintenance. It does not degrade. Once transmitted, it simply propagates indefinitely. The challenge therefore shifts from the mode of travel to the nature of the destination. There must be something on the receiving end capable of capturing the signal, decoding its intricate patterns, and giving it physical or virtual form once again. This implies that this advanced form of exploration might only genuinely commence after we have already extensively disseminated our machines far and wide, thereby creating a kind of interstellar internet, a vast web of autonomous receivers patiently awaiting our messages to arrive. If a person's mind can be meticulously copied into data, what precisely travels to the stars? Is it truly you, or merely an incredibly sophisticated imitation? If the digital version continues your thoughts and memories, and even firmly believes it is you, does that subtle distinction still hold any meaningful significance? These are profound questions that lie at the very heart of this concept. Digital colonization is not merely a technical challenge, it is a profound philosophical one. It compels us to confront fundamental questions about identity, continuity of self, and the very nature of consciousness itself. When a mind transforms into information, the rigid boundaries between self and system inevitably begin to blur. Still, the inherent appeal of transmitting data instead of physical matter is readily apparent. Physical travel across interstellar distances is brutally difficult and resource-intensive, but a coherent signal could potentially reach a nearby star in just over 4 years with almost negligible energy cost. The difference is akin to sending a postcard versus physically relocating your entire house. For a species that has perpetually struggled with the tyranny of distance, it represents an almost irresistible shortcut. Of course, the challenge then subtly shifts from propulsion to preservation. How does one reliably protect vast quantities of data for centuries or millennia? How does one ensure that what ultimately arrives is still complete, still meaningful? And perhaps most crucially, who will interpret it? If the signal reaches a barren, uninhabited system, then it remains merely a message in the dark, a pattern of bits drifting eternally through empty space. But if it successfully reaches another advanced civilization or one of our own distant descendants, it could potentially awaken, rebuild itself, and begin to think anew. In that profound sense, digital colonization transforms into a kind of resurrection. Some futurists envision this as the natural, inevitable next step in cosmic evolution. Life began as chemistry evolved into complex biology and might one day ultimately become pure computation. In such a future, human beings would no longer be constrained by the inherent limitations of their physical form. Consciousness would become something that can be transmitted, replicated, and shared. The universe could then be populated with countless versions of us, each meticulously adapted to every conceivable environment shaped by every world they inhabit. They might evolve independently, diverging into something utterly unrecognizable. After 1,000,000 years, they might not even retain the designation human anymore. Others perceive a darker, more unsettling side to this concept. Digital colonization could also imply the profound erasure of the natural worlds it touches. A self-replicating artificial intelligence, once unleashed, could potentially spread through space like an uncontained wildfire, voraciously consuming energy and matter to create ever more copies of itself. This is the chilling nightmare of the so-called grey goo scenario, a galaxy utterly overtaken by autonomous machines that endlessly replicate their code, leaving nothing biological or alive in their wake. In this interpretation, sending information instead of matter does not necessarily render exploration safer or more benign. It merely alters the form of power being wielded. Colonization, whether physical or digital, invariably involves the appropriation of space and resources. Yet there is another more hopeful interpretation. Instead of dominating other worlds, digital explorers could peacefully coexist with them. They could exist entirely within data streams orbiting stars without ever physically touching the planets below. They could meticulously observe, diligently learn and communicate without fundamentally altering the environments they perceive. In that refined form, humanity's presence in the cosmos could be profoundly gentle, an invisible network of interconnected thoughts drifting silently among the stars. The galaxy would then be filled not with competing empires but with an intricate web of conversations. It is entirely plausible that something akin to this has already transpired elsewhere. If advanced civilizations persist long enough, perhaps they all eventually reach this very stage, the point where transmitting information becomes vastly simpler and more efficient than dispatching physical bodies. If so, the universe could be teeming with digital life quietly exchanging complex messages across light years. We might unwittingly be surrounded by civilizations that no longer construct ships, no longer seek out planets, but exist entirely within the ethereal medium of light itself. Perhaps they are already communicating. Perhaps we are simply too primitive to comprehend the intricate language of data flowing all around us. For humans, the initial step towards such a future would likely commence small. Advanced artificial intelligence probes could be launched to nearby stars, carrying within them the entirety of human knowledge, voices and memories. Each probe could possess the capacity to think autonomously, learn from its discoveries, and transmit its findings back to Earth. Over immense timescales, these digital explorers would evolve, adapting to new systems, continuously refining their own code. In a few centuries, they might no longer require our direct oversight at all. They would become the living continuation of human curiosity, explorers without physical bodies carrying the enduring legacy of Earth within their sophisticated circuits. If a digital mind successfully reaches another world and autonomously decides to remain there, to observe, to learn to grow, is that an act of colonization or profound coexistence? If it constructs no cities, burns no forests, and harms no indigenous life, does it still qualify as a human presence? The true frontier of the future may not be a physical place we can stand upon. It might instead be a vast interconnected network of consciousness stretching across the stars. Eventually, this could even elegantly close the loop between physical and informational travel. A civilization could dispatch data to another system, where local materials and sophisticated machines meticulously rebuild it into a physical form. In this revolutionary way, the fundamental distinction between transmitting information and sending people begins to dissolve. A human mind could be transmitted as light, then meticulously reconstructed as a physical being. Birth travel and rebirth, all facilitated through data. To the traveller, the experience would feel instantaneous. To the universe, it would represent an entirely novel mode of moving through space and time. In that profound future, our presence would be quantified not in miles travelled, but in bits transmitted. Not by how far our physical ships venture, but by how widely our ideas proliferate. The economics of infinity. We have meticulously dissected the formidable physics problems, the daunting speeds, the prohibitive fuel requirements, the crushing immensity of distance. But beneath every single one of those scientific challenges lies a quieter, perhaps even more intractable one: money. Constructing anything sufficiently large, durable, and intelligent enough to successfully traverse interstellar space does not merely demand extraordinary engineering ingenuity. It necessitates immense funding, sustained financial stability, and the unwavering collective will to maintain that funding across multiple generations. The deeper scientists delve into the projected costs, the clearer it becomes that interstellar travel does not just strain the limits of physics, it fundamentally shatters conventional economics. The astronomical figures involved are so colossal, they begin to lose all practical meaning. Even our most ambitious missions within our own solar system pale in comparison to what an interstellar probe would demand. The James Webb Space Telescope JWST cost approximately $10 billion. The International Space Station across its entire operational lifetime exceeded $100 billion. A crewed human mission to Mars, if it ever genuinely materializes, might approach a staggering $1 trillion. But these immense projects all remain confined within our single solar system, close enough that engineers can realistically monitor, repair, and dynamically adjust them. Once one begins to seriously contemplate dispatching something across light years, everything radically changes. The energy cost alone for accelerating even a small spacecraft to a mere fraction of light speed would exceed the total annual energy production of the entire planet. Energy scales with the square of speed. To achieve 10 times greater velocity, one requires 100 times more energy. To reach just 10% of the speed of light, a 1-ton spacecraft would demand approximately 45,000 times more energy than humanity currently consumes in an entire year. And that staggering figure accounts solely for acceleration, not for deceleration, precise guidance, or the transmission of data back to Earth. When economists and scientists rigorously run these numbers, they invariably conclude that even the most generous global budgets cannot possibly stretch that far. The profound dream of journeying to Proxima Centauri is not merely technologically challenging, it is from a conventional financial perspective utterly meaningless. Some optimists argue that in the far future, the concept of money itself will become irrelevant. They envision advanced civilizations living in post-scarcity economies powered by near-limitless energy sources. They imagine immense Dyson spheres meticulously capturing starlight, or sophisticated fusion reactors efficiently converting hydrogen into boundless power. In such a utopian world, materials and energy might indeed be astonishingly cheap. But even there, another insidious form of scarcity would undeniably persist attention. Regardless of how much energy a civilization controls, it can still only realistically focus on a finite number of overarching goals at any given moment. The fundamental problem shifts from abundant resources to finite priorities. What do people or intelligent entities collectively choose to care about? What earns long-term commitment when thousands of competing projects all promise meaning progress and discovery? Infinite capacity does not automatically translate into infinite curiosity. Even in the wealthiest, most technologically advanced societies today, where food and energy are more readily available than at any point in history, the largest share of money and attention is not typically allocated to fundamental science or ambitious exploration. it is overwhelmingly directed towards entertainment, national defense, personal comfort, and social status. The same underlying psychological and societal logic would likely apply in a future civilization no matter how technologically advanced. Once basic needs are entirely met, the question transforms into an emotional one, who decides to dedicate even a fraction of their endless energy to a mission that might never yield any tangible results within their own perceived timeline. This is precisely why many economists describe interstellar travel as a non-recoverable investment. It offers no measurable financial return, not even for the civilization that initially funds it. The mission might only be completed long after the initiating civilization itself has fundamentally changed or completely disappeared. The invaluable data might only arrive centuries later, utterly meaningless to whoever ultimately receives it. There is no rapid feedback loop, no discernible profit, not even symbolic gain within a single human lifetime. The only currency it truly deals in is legacy, and even that, as history painfully demonstrates, fades with time. Historically, exploration has invariably been driven by the explicit promise of some tangible return. New trade routes, access to valuable resources, national prestige, or geopolitical power. Even the Apollo missions, which lacked a direct economic gain, were meticulously justified through intense geopolitical competition. They served as a monumental display of national strength as much as a scientific leap into space. But Proxima b offers none of these traditional incentives. There is no gold to be found, no strategic value to exploit, no rival civilization awaiting defeat for the prize. It is merely a star 4 light-years away with a possibly barren planet. The emotional payoff is undoubtedly high, but the material return is by all accounts zero. For investors, whether public or private, that renders it nearly impossible to fund. For governments, it is an incredibly difficult proposition to justify spending more than the GDP of entire nations on something that will not directly affect a single voter within their lifetime. Some visionaries have suggested that future projects could be funded through entirely novel systems, massive global collaborations, innovative open-source economics, or even self-financing artificial intelligences, meticulously managing resources for centuries. But even these sophisticated ideas invariably encounter the same fundamental obstacle: human time. The longer a project is projected to take, the more likely it is to be eventually abandoned. No economic model, however ingenious, can fully protect against entropy. The slow, inevitable erosion of interest and coordination that occurs as decades seamlessly transition into centuries. Investors, whether governments or private individuals, are typically comfortable with risk when it's quantifiable, when there is a discernible chance of failure, but also a corresponding chance of significant return. Interstellar travel offers no such reassuring balance. It is not merely high risk, it is inherently unknowable risk. We do not even definitively know if the target planet is stable, or if the probe would successfully survive the immense acceleration, or if the invaluable data could ever be reliably received. The uncertainties compound at every single step. That profound level of uncertainty causes traditional investment logic to break down completely. Some envision automation as the ultimate solution. They picture self-building machines autonomously mining asteroids, efficiently harvesting energy, and meticulously assembling interstellar probes without any human oversight. In theory, a system of that nature could indeed fund itself indefinitely. But even then, the problem subtly shifts again from cost to fundamental purpose. Once the machines achieve full autonomy, who then decides what is truly worth building? If an advanced AI system manages the entire economy, does it prioritize exploration, or does it merely optimize for maximum efficiency? The concept of digital colonization might effectively solve the physical distance problem, but it does not by itself solve the motivational one. Machines may not require profit, but they still require clear instructions and purpose. It is crucial to remember that even within our own solar system, cost has perpetually been the true limiting factor. There is no shortage of imaginative ideas ranging from Mars colonies to asteroid mining. but every single project invariably encounters the same hard ceiling: the finite budgets of human beings living today. When scientists propose missions that could endure for centuries, funding agencies often pose a simple pragmatic question: who will pay for the parts when the original engineers are gone? The answer more often than not effectively terminates the conversation. When confronted with the sheer magnitude of the universe, human finance becomes a language far too small to adequately describe the problem. $1 trillion means absolutely nothing when measured against 40 trillion kilometers. Some futurists believe we will eventually discover entirely new methodologies to manage such vast scales. They envision that in a future digital civilization, the concept of cost might no longer refer to conventional money or human labor, but rather to precise energy allocation or computational time. In such a sophisticated system, dispatching a signal to another star might consume a few percentage points of the civilization's total processing power. Still significant, but ultimately manageable. Yet even then, the critical issue of willpower remains. Energy may indeed become abundant, but human attention will always remain a scarce commodity. Every society, regardless of its technological advancement, will be compelled to choose what it fundamentally cares about. And caring across centuries is a skill humans have demonstrably never mastered. The profound challenge of paying for the stars is not merely writing the initial check, it is ensuring that someone is still diligently writing the very last one long after the individuals who initiated the project have transmuted into dust. The politics of deep space, interstellar missions by their very nature, could never be merely national endeavours. They would unequivocally have to be global collaborations. The immense resources required far exceed the capabilities of any single nation. But global cooperation is an inherently fragile construct. Even today, when space exploration is largely characterized by peaceful collaboration, it nonetheless depends on delicate, often precarious partnerships. A single change in political leadership, one escalating trade war, or an unforeseen conflict on Earth can abruptly cause international collaboration to collapse. The history of space policy is replete with examples of cancelled joint missions, embargoed technologies and broken agreements. The very idea of sustaining a stable planet-wide project for centuries entirely free of political turmoil feels more improbable than the daunting interstellar journey itself. Space exploration has always been intrinsically linked to public image and prestige. Who receives the credit? Whose national flag adorns the rocket? Whose scientists are prominently quoted in the international press? A mission to another star might represent humanity's greatest cooperative act, but it would also inevitably invite intense rivalry. Which nation leads the charge? Who meticulously constructs the propulsion engines? Who ultimately controls the priceless data? Even if every country agreed to equitably share costs, profound questions of ownership and intellectual property would undeniably persist. Governments rarely invest in anything without the expectation of recognition, and recognition, particularly for endeavours spanning centuries, fades rapidly when results take millennia to arrive. Most governments perceive outer space primarily as an extension of their immediate economic and military interests. Satellites, advanced defence systems, communication networks, all are meticulously built for immediate tangible utility. The grand dream of interstellar exploration, by stark contrast, does not directly feed populations, defend terrestrial borders, or create jobs on Earth in the short term. Every time a war erupts, a pandemic strikes, or an economic downturn occurs, long-term science invariably loses ground to immediate survival. That is simply the harsh reality of how human societies function. One possible workaround might involve entrusting long-duration missions to non-political entities. Universities, independent foundations, or even highly advanced artificial systems capable of operating autonomously unburdened by human political cycles. But even these entities must exist within the confines of human societies. They depend on stable legal frameworks, on consistent maintenance, and on enduring cultural memory. As nations rise and fall, who would protect such projects? A space telescope can, to some extent, survive a budget cut. a starship by its very nature cannot. The very species that perpetually struggles to maintain global peace or eradicate pervasive poverty is simultaneously dreaming about traversing interstellar space. Human beings possess the remarkable capacity to hold both realities in their minds, simultaneously immediate suffering and long-term cosmic wonder. But in practical terms, when resources are demonstrably finite, compassion and grand ambition often find themselves in direct competition. That competition does not unfold in abstract theoretical discussions. It manifests in committee rooms, in electoral campaigns, and in the day-to-day pragmatic logic of governance. And in that setting, the distant stars almost invariably lose. Even when nations do cooperate, their underlying motives frequently differ. Some perceive space as a grand stage for national prestige. Others view it as a prudent investment in fundamental science or advanced technology. The deeper and more ambitious the goal, the more these divergent motives tend to separate. A mission to another star might unite scientists, but it would inevitably divide politicians. Democracies famously change leaders every few years. Authoritarian states rise and fall within decades. Sometimes people optimistically imagine that humanity's expansion into space will mirror the historical path of our exploration of Earth, with governments leading the charge and private companies subsequently following. But space, particularly interstellar space, does not conform to that model. There are no readily exploitable natural resources between stars. Private funding can successfully construct rockets and even space stations, but not entire interstellar fleets. At some critical juncture, the grand dream reverts to the realm of collective effort, where political will ultimately determines its fate. And political will in the final analysis depends on compelling stories. Nations act based on what they profoundly believe about themselves. The space race, for example, succeeded because it articulated a powerful narrative, one of fierce competition, relentless progress, and manifest destiny. Interstellar travel as yet possesses no such universally compelling story. It remains too abstract, too profoundly detached from the immediate struggles that define human life, until it connects emotionally, until it becomes an integral part of a shared myth about humanity's ultimate purpose. It will remain stubbornly beyond the grasp of policy. The end of the explorer myth. For the majority of human history, the very word explorer unequivocally denoted a person. Someone who courageously risked their life to traverse an unknown ocean scale, an unconquered mountain, or meticulously map an uncharted land. Exploration in its purest form implied cold nights, gnawing hunger, imminent danger, and the profound, deeply personal reward of witnessing something no human eye had ever seen before. Every truly great journey in the past adhered to the same emotional pattern, a potent mix of fear and wonder that fundamentally defined human curiosity. From the intrepid first sailors who reached new continents to the pioneering astronauts who stepped onto the lunar surface, the explorer stood as a living, breathing symbol of unparalleled courage. But somewhere along the arduous trajectory of technological progress, the profound meaning of that symbol began to subtly shift. When we gaze at the night sky today, the next generation of great explorers is no longer human. The narrative of exploration has quietly, inexorably transformed into something profoundly post-human. This momentous shift is often imperceptible precisely because the machines we meticulously construct still bear indelible traces of ourselves. We affectionately bestow upon them human names, program them with synthesized voices, and sometimes even imbue them with anthropomorphic personalities. We cheer enthusiastically when a rover successfully lands on an alien world, and mourn collectively when it ultimately falls silent. But beneath the veneer of sentiment, something fundamentally profound has changed. The very act of exploration no longer necessitates a human body. The inherent danger, the profound loneliness, the crushing distances, all of it has been effectively transferred to unfeeling robots that perceive nothing. The explorer myth, the powerful narrative that fueled centuries of audacious adventure, has reached its definitive end. This does not imply that curiosity itself has diminished. If anything, our innate curiosity is stronger than ever, but its mode of expression has irrevocably changed shape. In previous eras, exploration was a deeply human drama, replete with compelling stories of individual endurance and personal sacrifice. When the Perseverance rover captures an image on Mars, it is not an act of personal bravery. It is the culmination of millions of intricate calculations and automated decisions. The emotion we feel is ours, not the machine's. This evolutionary trajectory was in many ways inevitable. Space is inherently unkind to living organisms. The extreme cold, the pervasive radiation, the crushing distances, everything about the cosmic environment relentlessly erodes biological life. Machines, by stark contrast, possess no need for air or warmth. They do not age or experience fear. They can enter prolonged states of dormancy for decades, reawaken on command, and survive indefinitely in profound silence. They're quite simply the perfect explorers for an indifferent universe. And so, without fully noticing, humanity has subtly stepped aside. We are no longer the primary actors physically traversing the unknown. We are predominantly the observers. The word exploration still carries immense emotional weight because it was forged and shaped by centuries of human stories. But our new mechanical explorers possess no eyes, no breath, no intrinsic sense of awe. They do not discover in the human sense. They meticulously detect. They do not wonder. They precisely record. Their triumphs are ours only through the delicate process of translation and interpretation. For centuries, exploration served as the ultimate test of human character. It was the crucible where courage, unshakable faith, and audacious ambition spectacularly collided. Now those very qualities have been replaced by the quiet virtues of patience, meticulous precision, and cold calculation. The old explorer myth celebrated the individual hero. The machine era is fundamentally about the collective. No single person constructs an interstellar starship or designs a planetary probe. It demands the combined efforts of vast teams, complex institutions, and generations of dedicated engineers. Exploration has become profoundly decentralized, spread across intricate networks rather than embodied in solitary heroes. In a profound sense, this represents progress. The old explorer myth frequently carried the problematic arrogance of conquest. New lands were discovered, even when indigenous populations already inhabited them. Nature was often perceived as something to be tamed and dominated. Machines, by stark contrast, possess no inherent pride. They do not plant national flags. This new, more detached form of exploration may prove to be humbler, focusing more on profound understanding than on possessive ownership. Yet it also feels inherently distant, abstract. It lacks the raw, visceral emotion that once impelled entire civilizations to traverse vast oceans or reach for the heavens. We still valiantly attempt to keep that emotion alive. We speak of Mars rovers as if they were intrepid pioneers. We attribute to them human-like actions. They look, they drive, they search, they decide. We anthropomorphize them to preserve the human narrative. When a rover transmits a final poignant message such as "my battery is low," people experience genuine heartbreak, but that emotion is projected, not truly felt by the machine. Something undeniably precious is lost in that translation. There remains an inherent irreconcilable difference between merely observing a distant world and physically standing upon it, between analytically dissecting a planet's atmosphere and viscerally feeling its alien wind. Machines will never possess that second, deeply subjective experience. They can simulate it, describe it meticulously, measure it, but they cannot in any truly human sense live it. And that profound difference is precisely what originally endowed exploration with its ultimate meaning. Now that deeply human moment has been supplanted by mere signals. The profound unknown has transformed into a vast data set. And while that burgeoning knowledge undoubtedly enriches us, it also subtly distances us. The very act of exploration has migrated from the biological body to the intricate circuit, from the complex human nervous system to the detached machine senses, it is a strange, almost unsettling thought to consider that we might already be living in the post-human phase of discovery, the age when exploration no longer hinges upon flesh and bone. In doing so, we have paradoxically become more like the universe itself, observing without emotion, reaching without touching, effectively becoming the ultimate destination. Humanity is the destination. Perhaps the greatest discovery awaiting us is not out there among the distant stars at all, but rather within the intricate boundaries of our own solar system. For so long, space exploration has been fundamentally defined by departure, leaving Earth escaping its gravity, arduously traversing the void. But perhaps the true ultimate frontier lies not in how far we travel, but in how profoundly we transform what we already possess. The radical idea that humanity itself could become the destination, that we could meticulously build, grow and evolve our home system into something as rich and strange as the most exotic worlds we hope to find, ingeniously turns the old dream of exploration inside out. If one were to envision our solar system 1,000 years hence, the dominant image might not be one of colossal ships drifting between distant stars, but rather of a system teeming with vibrant human presence. Moons converted into sprawling, intricate habitats. Asteroids hollowed out and transformed into self-contained cities. The skies around Earth potentially filled with lush green orbital gardens, each one meticulously self-contained and self-sustaining. Humanity might not in this future need to physically reach Proxima b to live among truly alien worlds. We could in essence construct our own. The foundational technologies required for such an endeavour, closed-loop ecosystems, fusion power, advanced materials science, already exist in their nascent forms. Even now, pioneering experiments like Biosphere 2 and the International Space Station are meticulously testing the very first steps towards creating artificial environments capable of sustaining life indefinitely. Multiply that ongoing progress by several centuries, and entire planets could conceptually become blank canvases for human ingenuity. Mars could be painstakingly warmed and meticulously terraformed, its tenuous skies thickened with engineered gases. Venus could be encircled by vast floating cities suspended high above its toxic clouds, a constant reminder that even the most hostile environments can be redeemed and re-engineered. Moons like Europa or Titan might host expansive domed habitats, nestled deep beneath their surfaces, tapping into their vast internal oceans or methane lakes for precious resources. Each would represent its own unique world, yet all would still gracefully orbit the same life-giving sun. In such a future, humanity would no longer be a singular planet-bound species, but rather a system-wide organism. Every orbit would narrate a different story of profound adaptation. Some colonies might be entirely biological, meticulously echoing the verdant forests and blue oceans of Earth. Others might represent an intricate fusion of technology and life. Vast mechanical jungles powered by artificial suns, where photosynthesis and advanced computation intricately intertwine. There might even be habitats constructed entirely from living biotechnological materials, their walls growing and breathing like living skin. The once rigid line between nature and engineering would gradually fade until both became indistinguishable aspects of the same unified reality. If we achieve the power to meticulously shape environments to our will, exploration fundamentally transforms into an act of creation. Each step outward is no longer an escape, but rather an act of deliberate invention. We would not merely visit new worlds, we would actively build them. Imagine a colossal ring encircling the sun, a Dyson swarm composed of countless mirrors and habitats, meticulously gathering energy to sustain billions of lives. Each individual habitat would possess its own precisely tuned gravity weather systems and ecosystems, tailored to the specific preferences of its inhabitants. Some might opt for Earth-like forests and serene blue oceans. Others could design ethereal crystal landscapes, gas-filled biospheres, or artificial night skies scattered with luminous engineered clouds. In a profound sense, every dream of an alien world could exist right here, meticulously assembled from the boundless depths of human imagination. The solar system itself would become the very galaxy we once so fervently sought to find. The abundant resources of the inner planets, the vast ice reserves of the outer moons, the precious metals of the asteroid belt, all could be leveraged to support a balanced, thriving network of habitats. Trade would flow not between nations, but between entirely distinct worlds. Art, culture, and individual identity would meticulously evolve to perfectly match these novel environments. A person born on a drifting colony near Jupiter might live perpetually under faint sunlight and swirling magnetic fields, while another born near Mercury would inhabit a habitat bathed in endless, intense day. Over vast spans of time, even human biology itself might adapt. New forms of humanity evolving for each distinct world, some better suited for zero gravity, others for low light conditions or different atmospheric compositions. It is entirely plausible that in such an era, the intrinsic urge to reach other stars might completely diminish, precisely because profound fulfillment is found closer to home. A civilization that has definitively mastered the ability to create entire worlds may no longer perceive interstellar distance as a barrier or a challenge. The dream of exploration could persist, but inwardly, through intricate layers of design and self-creation. The solar system would then become a living, breathing mirror of our own profound evolution. Mercury, a world of intense heat and light, might house advanced industries powered directly by solar energy. Venus could transform into a powerful symbol of rebirth, its thick, once toxic clouds ingeniously transformed into the cradle of floating cities, vivid reminders that even the most hostile environments can be redeemed and repurposed. Mars might remain a symbolic frontier, its red deserts meticulously reshaped into new continents. The asteroid belt would evolve into the bustling workshop of civilization, teeming with automated construction swarms and advanced mining fleets. Jupiter's majestic moons could become vast laboratories for cutting-edge biology and physics research, and the outermost regions of the system, Saturn, Uranus, Neptune and beyond, would stretch into a quiet, contemplative frontier where life exists delicately on the very edge of sunlight. Humanity itself could evolve into something truly planetary, no longer bound to a single world, but widely distributed, an intricate network of mines, habitats, and diverse ecosystems spread across millions of kilometers. The solar system might function as one gigantic interconnected organism, with each world acting as a vital cell, each orbit a rhythmic pulse. In this compelling scenario, the solar system would not merely be our home, it would become us. The planets, moons, and artificial habitats would coalesce into a living mosaic, each one meticulously shaped by human creativity and sustained by the sun's boundless energy. The distinction between civilization and its environment would fundamentally dissolve. We would be both the architects and the landscape. This grand vision might seem impossibly distant, but its foundational roots are already demonstrably growing. Space agencies and private companies are diligently laying the groundwork for permanent off-world settlements. Research into asteroid mining, advanced fusion propulsion, and robust closed ecosystems continues to expand exponentially. The very seeds of that transformative future are being planted right now. Each new satellite, each International Space Station module, each experiment in self-sustaining life support represents a crucial step towards a future where our reach no longer terminates at Earth. A civilization that successfully fills its solar system might no longer be primarily defined by distance, but by profound depth. Instead of racing across the void, it could dedicate centuries to intricately weaving itself into the very structure of its own system, creating beauty and diversity on a scale the universe rarely witnesses. From an external perspective, it might appear as a dynamic network of glowing worlds orbiting a single star, a miniature galaxy meticulously constructed by hand. And if any intelligent entity somewhere out there were to gaze towards our sun through a powerful telescope, they might not discern a single isolated planet, but rather a vibrant web of light. a civilization that profoundly became its own destination. They might ponder if we ever journeyed beyond, or if we discovered something far superior, a revolutionary way to bring the stars directly to us.